Good morning to all of the participants, speakers, and the chairperson for the Day 3 conference of Indian Academy of Physical Sciences, Advances in Physics, organized in association with Gondwana University, Gadchiroli, Maharashtra, India. Good morning, Professor Michael, sir.
Good morning. Good morning.
Good morning, sir. Good morning, Gedam, sir.
Good morning, sir.
Let us now it's time. I think it is 10:05. I think in as per Indian timing. So let us start the first session. So before starting the first session, I would like to uh, introduce today's uh, chairperson for this session. Today with we have Professor S.C. Gedam. He has 23 years of teaching experience. He is working in KZS Science College, Kadmeshwar, Nagpur, India. He is a PhD guide. To his credit, he have 75 international publications in reputed journals, and in conferences he has pub, uh, and in conferences to his credit there are more than 200 papers. 8 PhD students have been awarded PhD under him. So this is the short introduction and biodata of Professor S.C. Gedam. Sir, Gedam sir, I now request you to
Yes.
chair the session, sir. Please.
Okay. Thank you very much, sir. Can I start, sir?
Yes, sir. Yes, sir. Over to you, sir.
Okay. Okay. Thank you very much, Dr. Kage, sir, for kind words. Good morning to everybody. Good morning to organizers, and thank you for invite me as a chairperson. Now, I welcome you all in the first session of last day of this conference. For this session, we have two great personalities, that is Professor Michael Sivajarvi sir from Sweden and Professor Muhammad Imran Asgar sir from Hubei University, China. When I see towards the career of both scientists, it's just amazing and really splendid achievement by both scientists. And it's a great thing for us to have you here, sir, for this particular event. I welcome both of you, sir. So without spending their valuable time, I must introduce our first speaker, Professor Michael Sivajarvi sir. Sivajarvi sir has two affiliations. Main affiliation is Alimika AB Sweden and other affiliation is Linköping University Sweden. On a semiconductor and nanotechnology materials for energy and environment, crystal growth and material process. He did his MSc degree in 1994 from Linköping University, doctoral degree in 1999 from the same university. There are so many grants and projects in his credit. Also, he published more than 256 papers in international journals. His international involvement as a collaboration partner is remarkable. Supervise PhD students, postdoc supervision, industrial research supervision, as well as MSc thesis work supervision. He organized so many conferences. He received some prestigious award also, that is International Union of Crystallography Young Scientist Award in 1998, Scientist Medal of the Year 2014, etc., and many more. He delivered so many invited talks in various conferences. He published 9 books and chapters and books. He published 9 books and chapters in books and many more. So I must say nothing is remained behind again in his field. He achieved everything. Now, Professor Mikhail Sivajarvi sir, everybody is eager to hear you, sir. and therefore I am requesting you to deliver your popular talk. Welcome, Professor Shivaji sir.
Thank you very much, Dr. Gedam. This biography is something which has been collected during many years since 1995. So it may seem to be many things which are there, but this is because it's over time. It's many things which are done, and of course, always there's collaboration in team and so on. So this I focus more and more on to have exchange with other people, both in our direct collaborations and partnerships, but also in new ones. And therefore, I'm very happy to be at this conference and present some of our findings in order to disseminate our results, but also to open up for new collaborations which are possible. And since some time, I've been very active with the Sweden-India exchange because I think they are natural platforms, and we already have some ideas using virtual lab on our material. So now I will share some of the ideas which are in happening in our lab and so on. And hopefully now you can see the screen of my presentation. Yes, good. And I will focus on carbon as a material for new research avenues. And if you happen to follow the Nobel Prizes, you see that in the physics, in the chemistry and medicine, carbon is very often there. And this is because it's one of the most natural materials, but it has very nice properties. So like in medicine chemistry, it's either bonding of carbon to each other or breaking the carbon bonds to make something new, and then you have some possibilities for that. So carbon is a natural material. And in my case, I work with silicon carbide growth, and then we have this schematic of the traditional growth process. So in this one, there's a source of silicon, silicon carbide, and that contains the silicon and carbon. And when it's heated up, the vapor species are transported to the growing surface, and the crystal is growing. So this is the basic principle. And now, since the 90s, when it was initiated a lot of studies in silicon carbide, it has developed. So you have 6-inch wafers available from this process, and there's a market. So this PVT process is very established. And what we did was we modified this method to make a shorter distance and having a ceramic silicon carbide instead of a powder type of silicon carbide. And then we came into new avenues of silicon carbide growth. And just an example how things can spin off to new things is that in this growth method, here we have a ceramic silicon carbide as a source for a wafer of silicon carbide. So there's a distance, so then we can grow thick layers. So this type of thick layers is the outcome of the intentional research there. But then we are using this ceramic silicon carbide as source material, and this is available. This is used as dummy wafer for silicon growth and other things. And then we came into another avenue where there was a request to have 2 such wafers, but they should be bonded to each other, and there should be a cavity in between them. So instead of doing growth as for thick layers, we try to bond these 2 together. And this interest came because when you want to use higher temperatures in engines, then this is attractive for sensors, so you can follow the process and correct it much more faster when you're using these high temperatures. And then silicon carbide is a material which is good for high temperatures. So in that way, we came into another avenue of bonding wafers to each other instead of making thick films. And this has interest both for fossil fuel, but also for biofuels. And this is an example how we have bonded two wafers to each other for this process. But this is very initial stage. But I wanted to show this as an example of how things can turn out when there are new things coming up. And also this is interesting to control in the shipping. You need to reduce for the climate problem and so on. So this you need to control. So there's a lot of motivations for continuing this research. And carbon. So if you maybe recognize these guys, they got the Nobel Prize for the graphene in 2010. And graphene is one layer of carbon, which is now very much explored. And the scientific community just bursted into this research avenue because graphene has so many different application avenues, both from the electronics and so on, but also to be included in composites or used in other. So the number of branches which graphene can be in is very, very many. And of course, like all materials, in the beginning, there's a lot of need to study the growth of the material, there are defects, and so on. So this became a really interesting avenue for all over the world. And there are various ways to make this graphene. The traditional or Nobel Prize type of process is that you have graphite, and then you have Scotch tape, and then you remove the graphite, and then you make this removed piece thinner and thinner and thinner in a repeated process. And at the end, you have one layer of carbon by this. And then you have small flakes, which you can study. And this is what the Nobel Prize winners did. They had used the Scotch tape removed, and then they got the Nobel Prize. Of course, it's not just like that, because what they did was a very process which took a lot of time and patience, but then they also explored the properties and could demonstrate that once, and they made the theory, and then they had a package to deliver, and then they got Nobel Prize. So that's one way to make flakes, and there are other processes to make flakes. The second process is that you have a metal, and then you run a carbon-containing gas over it, and then you have one layer of carbon on the metal. And the idea is that you can remove this carbon and put it on some bendable polymer and so on, and then you can make electronics which are large size but bendable. But the quality of this graphene is difficult to control. So the third method or principle is to use the silicon carbide as wafer. It contains silicon and carbon, and when you heat up, a little more silicon is leaving than carbon, and then you have one layer of carbon on top of this wafer of silicon carbide. And all these things explored, and in Europe there is a flagship. So here's a discussion about the initiative for a flagship in graphene. So it's a big program with 1 billion euro, which is now collected into this program, which now wants to move the graphene from the material point of view to make components, and then to system and so on. So there's a 10-year program to shift the graphene from the research to the market. So this is what is happening in Europe and in many places of the world. But the graphene flagship is very nice to have. In our case, we are using the silicon carbide. So here's an example of a bowl which we have been growing with this first method, the original. This principle is the one which is important for the process. So we heat up, and then we have the vapor species which are formed. And there are various types of vapor species from the silicon carbide. So you have silicon 2 carbon, silicon 1 silicon and 2 carbon, and so on. So this is a delicate process, and when we use this for the growth, we have a ratio of silicon to carbon to be 1:1, and then we can grow silicon carbide. But if more silicon leaves, there will be more carbon, and then we can do graphene on silicon carbide intentionally with this process. So then we are using high temperature, and in case of silicon carbide, for this vapor species to be to occur, then it's very high temperatures, around 2000 degrees C. This process starts about 1500, 1600, and then when you go up at temperature, there are more vapor species which are formed. And for the bulk growth, we are using 2200 or 2300 degrees C for growing the boules. For the graphene, we are using a process around 2000 degrees C to heat up. So here you see a furnace which has a container, a susceptor of graphite, and inside there we have the process. So you see the glowing growth container, and that is the one which you're seeing here. So we cannot see the process directly, but it's very hot. And actually, in our silicon carbide, when there was thick layers grown, and then device people did ion irradiation and other things to dope the material to get p-n junctions and all those things which are needed for the electronics. Then when the crystalline material was damaged by the ion irradiation for the doping, then actually what was done was that we heated up some of those layers in order to improve the crystalline quality again, which was damaged by the ion irradiation. So this we did, and then we observed that there is a thin graphitic layers on top of this irradiated surface. And then one research group from Chalmers, they wanted to study these graphitic layers, and there was a publication that this graphite on silicon carbide has very high quality. And that was almost 20 years ago, which we did this for those purposes. And then what we did was to make this thin graphitic layer thinner. And then 2005, we observed one layer of carbon on top of silicon carbide. And then we had some collaborations doing simulation of the process and heating and so on. But that was the first time we observed monolayer of graphene on silicon carbide. But we did not know so much what to do with this and so on. But from the crystal growth point of view, it was very fascinating. And then we did some more studies. So we had a master thesis exploring this process. So we learned a little bit more on that in 2008. Was one student, and in 2010 we could control this growth of monolayer graphene in a quite good way. And then it was again collaboration with Chalmers and other organizations where they demonstrated the quantum resistance standard. So the quantum Hall effect on the graphene on silicon carbide was demonstrated for the quantum resistance, or towards the quantum resistance. And that paper showed that it was very nice effect because it was very nice quality of the graphene. So that, and then it became a paper in this Nature Nanotechnology, and we are not so used to publishing such distinguished journals, so it was very nice to have this publication. But that was 2010, so it was 8 years after the first thin graphitic layers. And in silicon carbide, this is a little bit tricky to have a monolayer graphene, because when you heat up the silicon carbide, you have various surfaces which are formed from the bilayers, silicon and carbon. When you stack them, you can have different ending surfaces for the 4H polytype and the 6H polytype. So you have small different steps. And this, of course, makes it more problematic to have monolayer graphene. But this is also a source of the graphene, because the graphene starts at the edge and not on top of the surface. So this we have studied a lot to understand how the silicon carbide behaves when it's heated up, when you have step bunching and all those effects. And my supervisor from the 90s, we have been collaborating together since 1995. We have explored this process, and she was the one who initiated the collaboration with Chalmers. So Rositsa Yakimova is a very knowledgeable person in growth, and we have had very nice collaborations and built up teams around these things. So here we have a process for graphene on silicon carbide on wafer scale, and actually there was so much interest in our material that we even had a company formed. So I have been very active to start a company for the graphene on silicon carbide as material, and that is now further developed by a CEO and organizations towards devices. And there, for the graphene on silicon carbide, the interesting thing is that when we have the nice quality of the material, then we can control the electronic function of it. So to have based on the quantum Hall effect. And then one of the avenues is that we make a sensor which can be very sensitive towards various gases or biomolecules when we functionalize it purposely. So sensing is one of the avenues for the graphene on silicon carbide. And there, again, we come back to the control of the surface in the growth, how we do this in the process, but we can also do additional things after growth, so post-processing, to modify the surfaces towards specific applications. And there we would like to have interaction with other molecules to be specific. And in the silicon carbide, this process, you have the different vapor species which are depending on temperature, and the steps are formed. So there's a range of influences. And when we heat up to different temperatures, the ratio of the silicon to carbon is changing depending on temperature. So this we can use to have monolayer graphene or even 2 layers and 3 layers, but then it's much more difficult to control. But this is one of the ways how to control the graphene, not only to monolayer, but also bilayer or other things. And the silicon to carbon ratio is important. So if you ever start to study the graphene on silicon carbide, these graphs will be very useful for you. And the steps which are formed are the basic problem, but also possibility. And the different steps which are formed depends on the different polytypes. So when you have the silicon and carbon, you can stack them in different ways. So then you can have 6H silicon carbide, the 4H silicon carbide, or the cubic silicon carbide. And the graphene on these ones are a little bit different for each polytype. So that broadens up the possible ways to modify the material in different ways. Now we are trying to do this and find some application areas where the specific polytype is unique in some type of application. And then the surfaces are modified in different ways, and they are not only regular straight steps. At some conditions, you start to have some waviness of the surface, which usually is very bad for the growth, because then the growth front start to become unstable and so on. But this we also can use this waviness to tailor the material in further ways. And when we look at the details of them, we see that there are these steps which are formed, but also the graphene which is formed. If it's damaged, it can fold and make 2 layers from one original layer. And when we do this in different ambients, like vacuum, argon, which we use to control the vapor species, then we get different things happening in the different polytypes. So this broadens up the various ways how we can grow the material intentionally. And even if you are using these steps and doing some certain processing before, then we can actually have 1 layer of carbon along the steps. So then there's monolayer graphene in one direction. So it's not covering the surface totally, but it's along these steps. And then we have ribbons of graphene on the silicon carbide. So that's also one way to explore this growth, to modify the material for new avenues. And we actually have, since 2015, I think, a collaboration Sweden-India. So Priya Kaushik has been visiting researcher with us since that time. And what she's doing is that we have the ion irradiation. You can have low energy, you can have high energy, you can have various ions which for the irradiations. So in this way, we can use the low energy to just irradiate the graphene and maybe the top surface. But if we're using higher energy, we actually irradiate into the silicon carbide. So we can irradiate the silicon carbide or the graphene on silicon carbide together with the silicon carbide, depending on the energy of the ions, but also which type of ions we are using. So this is a very nice collaboration which Priya is leading, and this is one of the things we will continue in our Sweden-India exchange. And now we are planning that we are using these type of materials for sensors, and since we have so many ideas, we cannot do experimental work on all of them, but then we can use a virtual lab to screen some of these things so we can focus on certain areas. So this is also a collaboration with Aparna Dixit, which is now growing in between Sweden and Silicon Carbide. So this is a platform of exchange. And in the case of the ion irradiations, when we have different ions and different fluxes and so on, then there's a different sensing which is triggered. So here we can see some graphs. I will not go into the details of these because I'm not the expert, but when we modify these, we can see that there is a sensing function towards different things. And we can tailor this, start to control it by the ion irradiation. And when we do these things in the different polytypes, there will be different things happening. So it will grow into different avenues. So this we can use to study. And maybe we don't need monolayer graphene always. Maybe we can have 1, 2, 3 layers in a combination intentionally to tailor towards new avenues. So that was the graphene on silicon carbide, and this is wafer scale large area. And then there is also the flakes of graphene, and the Scotch tape method is nice, but it's not very production friendly. So if we want larger volumes, then that is not so useful. So there are other ways. And here we are also interested, maybe we can take these different flakes, which are produced by different organizations. So they have different types of graphene, which are differ from each other in different ways. So if we could use those and combine it on top of our graphene on silicon carbide, we use our process to integrate them, then we can have additional functions of the material. So we stack material on each other for new ways, not only modify it in the growth. So maybe we could have like nanowires or other things. So this is another avenue we are moving into. And in Sweden, we have graphene since many years, and there's a Swedish innovation program, a national program, where graphene is moved. So this is like the flagship in Europe. This is similar, but in Sweden. So we actually have industrial graphene now available from the activities in Sweden. So SIO graphene is that program. And then a couple of examples is the 2D Fab. This is a company. They do this flake type of graphene in a production way, and they have a high volume process. I will not go into the details of that one because I'm again not expert. But this shows that we have available industrial graphene. So if we ever would like to commercialize our findings from the research, then we have reproducible material on our reproducible graphene on silicon carbide, which then makes that it's a higher probability that this can be used in production and commercialized. So 2D fab, they have different processes and different applications for that. And then they have a unique process where they now go into very high volumes. So that is one of the examples from what is happening. And they have different business areas which they trigger on, because you can do the material, but then you need to collaborate together to develop the applications. So this is always needed when you have material and you don't know exactly how it functions in an application. Then you need to collaborate together to understand this. Another example is Graphen AB, where they do actually graphene oxide and use that one. So Eric Karnowski is leading that one. So he's the founder. And in there, they have the graphene oxide, and they use this for metal removal in water, so heavy metals and so on. So there's a filter with the graphene which is used. So that material is also available. So these various graphene types, we would like to combine with our graphene on silicon carbide. So it's a source for different avenues. And then we can broaden up the possible applications. But of course, since we are not so many who are studying this, then we need to screen these ones. That's why this exchange with virtual lab and other things are needed. And at the end, everything is about collaboration. So we need collaboration with groups, and then we can focus on certain areas together. So we will not decide this ourselves, depending on our interest. Very much in research depends on who are collaborating, who are the ones who are having the exchange in a natural way. So those we try to follow also in the research to broaden up and build our CVs further from the original one. And there we have had quite actually much change with India in discussing research. So here is Manvendra Yadav. We had a startup weekend where we discussed things and the students were asking questions. I made the presentations, and it was also online. I think the first time was 2018. So this is a screenshot from my laptop. And also we have had visitors. So the chief secretary of Uttar Pradesh was visiting one of our research materials conferences and so on. So there has been natural exchange in different ways to build the platform. And also this year I got contact with Aparna Dixit on the ideas of the virtual lab and so on. So things are moving and growing in a natural way, and then we will have further projects. So this is why these exchanges, either at conferences, but also this online, is very appreciated. So that's very nice that I had the opportunity to share some things, and then we can discuss further from ideas which are emerging from this. And at the end, the motivations are towards gas sensing or biosensing for something good. So the climate and sustainability activities are very, very important motivations, driving force in the long term. So by this, I hope I have given you some introduction to my type of research, what I have been doing for many years. And it started with my interest in the growth of the material, and then we wrote papers and so on. And then I became more interested to find new avenues. And these are always done in collaboration. So when we find nice matching complementary, we can do something together and open up for new activities. So with that, I hope I have given you an example of what can happen. And it was not planned from the beginning to go all these ways and come to these avenues. It was, we were screening some things and then we followed these things. So that is also one example of how to do things. Then there will be opportunities, and we cannot plan that ahead because there are so many new things. But this is one of my sharing of experiences how to continue to do this. So with that, I thank you very much for listening and inviting me to this conference. Thank you. So do we have any questions from the panel or from in the chat box?
If you have any question, thank you, Dr. Professor Mikhail Shivajarvi sir. If participants have any questions or any doubt, ask to Professor Mikhail sir. Is there any question? Kage sir?
So there is for the attendees, they can write questions in the chat box. So for either for me, but also for the next presentation, during the presentation, they can write in the chat box and ask questions, and those will be answered at the end. And of course, when questions arise later, everyone is kindly asked to email me questions and so on, or ideas on collaborations or whatever. So this is very much appreciated.
Sir, there is one question on the chat box. What best response time of the sensors made by graphene?
Yeah, the response time is it's some minutes or seconds. I don't remember the exact details, and we have not explored that yet. But also there is the recovery after the response. Then when we clean the surfaces so we can use the sensor again, then we have to have the recovery of the signal so we can respond again. And that has been few minutes, in some cases a matter of more seconds, not few seconds in the research, but I don't remember all details. But this is something we would like to control. But the fast response is not the most important. It's more important to respond specifically at as low level as possible. For example, if we are using these sensors in the city to control the pollutions and get the signal, then we don't need very fast measurements. But we need to control this as sensitively as possible. So maybe we can use this signal or data from the sensors to control the traffic. So we can direct the traffic so there's less pollution over the city. And maybe we can even use this to have a digital twin of the city. So when we are changing the traffic, other things in the city can change their thing. So maybe this type of sensor. And then it's more important that it's specific and as sensitive as possible, because these changes are not super fast and so on. So that's one of my comments to that question.
Very much, sir.
No questions are there, sir, in the chat box. So we can proceed
Thank you very
further.
much. Uh, uh, for your innovative talk, the next topic, and the doubt. Okay. So, thank you very much, sir. Can I proceed to next
Thank you.
speaker, sir? Aage, sir.
Sir, yes, sir. Yes, sir.
Can I proceed, sir?
Yes, sir. Yes, sir.
Oh, okay. Thanks a lot. Well, next scientist, Professor Muhammad Imran Asghar, who is working as a faculty of physics and electronics science at Hubei University, China. In addition, he works in the Department of Applied Physics at Aalto University, Finland as an academic research fellow. He is awarded with prestigious fellowship by the Academy of Finland. He has also working in the Finnish industry as well. He worked in Morif OI and photovoltaic panel manufacturing company also. He completed his doctoral degree from Aalto University in 2012, master degree in 2008 from Helsinki University of Technology. He has expertise in ceramic, nanocomposite fuel cells, batteries, and other energy technology. He is also expert in digital printing technology also. He has published more than 65 international publications in reputed journals and conferences. He has supervised so many students for PhD degrees, master degrees, and bachelor degree. So, such a great personality with us, and I am requesting Professor Asghar sir to deliver the talk. Professor Asghar sir.
Thank you very much for a kind introduction. I hope you can hear me well.
Okay, well.
Yeah, thank you.
Yes, sir.
Okay, thanks. It's my pleasure to be part of this conference. Thank you very much for your invitation. So here are a couple of acknowledgements. So first of all, I'd like to thank the conference organizers, especially Dr. Ishwar for his kind invitation for the conference, and Professor Mikhail for his invitation, and also the session chair for your kind introduction. And then I like to thank Academy of Finland and Talent 100 Hubei Province, China, for supporting my research. So before I start my presentation, I would like to tell briefly about where I'm coming from. So basically, I'm coming from Aalto University, Finland, which is located in the north of Europe. So here you see like Finland is located in the north of Europe. Its population is about 5.5 million, the whole country population. And Finland is a beautiful country and is also known as a land of 1,000 lakes. So there are lots of lakes in the country. And here you see these northern lights in Finland, since we are located in the North Pole. So it's we can see these Nordic lights, which are really beautiful. And since we are located here and we have excellent connections to Europe, so there are lots of flights going to China, to India. And the amazing thing about Finland is that in summer, the days are very, very long. For instance, here you see some photos. So this is the photo from midnight. And you can see that still the sun is shining. And but it's the opposite in winter when we have nights like very long. And especially in Lapland, the sun doesn't rise for a couple of months. And same in winter, like sun doesn't rise, but in summer we have daytime all the time for a couple of months. So very amazing and beautiful country. And Aalto University is located in the Helsinki metropolitan region, very beautiful city. And here are some photos from Helsinki and from summer, and this is the photo from winter. But it's a very beautiful country and has direct flight connections with India. So I welcome you all to visit Finland. And briefly about Aalto University. Aalto University was founded in 2010, and it was a merger of three renowned universities: Helsinki University of Technology, and the Helsinki School of Business, and the University of Arts and Design. And there was a merger in 2010, and within a span of 10 years, now Aalto University international ranking is 9 in the young university category. And so it's basically Aalto University's motto is like we try to combine different technologies, arts, and businesses, and students are all located in one campus. And these kind of combinations really trigger the innovation in our research. And then I'd like to briefly talk about our research group. We are a team of about 20 researchers, and we have quite international team from different uh, countries. And Professor Peter Lund is the head of our group, and I have my own team here at Aalto University. And so and we are basically working on different topics. We work on solar cells, primarily dye-sensitized solar cells and perovskite solar cells. And then we also work on fuel cell technologies, mainly basically nanocomposite ceramic fuel cells, but also we have some other technologies, single layer ceramic fuel cells. And we are also working on future energy systems and energy frugality. And so these are the areas where we are working on. But today, my talk will be mainly focused on nanocomposite ceramic fuel cells. And I will also talk about the single layer fuel cells. So today the talk will be mainly on the fuel cell part. So I will not talk about solar cell and the energy systems. Here are basically the contents of my today's presentation. And first, in the first part, I will be talking about nanocomposite ceramic fuel cell research. I will talk about why they are important, what are the key research challenges, and what are the potential of this technology. In the later part of my presentation, I will be talking about single layer fuel cells. What are those single layer fuel cells, and what are the key challenges in research, and what are the performance limiting factors in these kind of fuel cells. And finally, I will draw some key conclusions and briefly talk about our next steps in research. So let's start with ceramic nanocomposite fuel cell research. So here you can see a schematic structure of a solid oxide fuel cell, which is also called ceramic fuel cell. The ceramic fuel cell is a promising fuel cell technology. And basically, this fuel cell structure, if you look at it, has three layers: anode, electrolyte, and cathode. On anode, we supply our fuel. It could be hydrogen or it could be any hydrocarbon. And on the cathode side, we supply oxidants. So oxidation reaction happens here, and the reduction reaction happens at cathode, and we get different ions. In electrolyte, only ionic conduction takes place, and it blocks the electrons. And as a result, we get these electrons as a result of these dot reactions, and the only byproduct of these reactions are basically water. If you're supplying hydrogen, the only byproduct is water. But if you're supplying any hydrocarbon, then you might get carbon monoxide or carbon dioxide. So it's a clean energy technology with water is the only byproduct. This is a promising technology. However, it has certain limitations. For example, it requires very high temperature for its operation. Typical operating temperatures are around 700 to 1000 degrees. And when we operate at this high temperature, we face certain challenges. We are limited by our choice of materials, and higher temperature also causes lots of degradation reactions. So in order to reduce those degradation reactions, we need to reduce this operating temperature. But the problem is when we reduce the temperature, the fuel cell performance also goes down, primarily due to limited ionic conduction. So this ionic conduction slows down when we reduce the temperature. And below 700, the ionic conductivity goes below 0.1 siemens per centimeter. So our nanocomposite fuel cell, our nanocomposite materials, they basically offers higher performance at lower temperature. And when I call lower temperature, I mean 400 to 550. So we reduce this temperature from 700,000 to 400 to 550, and we achieve the same or even better performance at lower temperature. So all this happens due to these nanocomposite materials. So basically, what are nanocomposite materials? Nanocomposite materials basically consist of a mixture of doped ceria, which is an ionic conductor, and we use alkali carbonates. And the main thing about these nanocomposite materials is that they exhibit multi-ionic conduction. In a conventional solid oxide fuel cell or ceramic fuel cell, we have only oxide ions, oxygen ions, which are basically conducting in the electrolyte. In our nanocomposite electrolytes, we have multi-ionic conduction. We have carbonate ions, we have these alkali ions, oxide ions, and even hydroxide ions and hydrogen ions. They all conduct, and as a result, the ionic conductivity improved a lot. And for example, here is one schematic about how this ionic conduction takes place. So here we see these different ions. They are conducting through different channels in the nanocomposite electrolytes. So in our electrolytes, there are different paths or channels through which these ions conduct in the electrolyte. And for instance, oxide ions, they can move through the bulk of oxide phase. There are certain ions that move on the interface between oxide and carbonate ions, so they move on the interface. So we have different channels through which this all different ions they conduct at the same time, and as a result, we get really improved ionic conductivity of our electrolyte material. So here we see different reaction schemes, how these fuel cells work. Here we have this schematic structure of our nanocomposite fuel cell. So here we have cathode, we have anode. So on our anode, we are supplying hydrogen, and on cathode, we are supplying oxygen, or in addition to oxygen, we can also supply carbon dioxide. So for example, if you look at the first reaction scheme, what happens is, like, when we supply carbon dioxide and oxygen, they are reduced at cathode, and as a result, we get carbon ion. And the carbonate ion, it transport through the electrolyte towards anode, and at anode, it reacts with hydrogen gas, and we get water and carbon dioxide, and we get electrons. And from electrons, we get electricity, and this carbon dioxide, it can be fueled back to the cathode side. So overall cell reaction, if we look at, it's basically water and oxygen react to give water. So this carbon dioxide cancels out because we use the same carbon dioxide at anode. Another reaction scheme basically is about these alkali carbonates. So here we supply hydrogen. So what happens is that these metal carbonates, basically there we get these metal ions as a result of this oxidation reaction. We get these metal ions, we transport from anode to cathode, and at cathode they react with carbon dioxide and oxygen to give these metal carbonates. So overall cell reaction again is the same, that we have hydrogen and oxygen, and it gives us water because these carbonates are kind of cancelled out. So regardless of different reaction schemes, the net byproduct is water. So this is a clean energy technology. We prepare our nanocomposite materials through different methods. Through solid method, then we have this core precipitation method, we have sol gel method, and Pecquenet method. So we are quite experts in designing the size of nanoparticles and controlling their properties by different reaction schemes. Without going in detail, I would like to tell that finally we get our nanoparticles, which are about 50 to 70 nanometer in size. And these are, for example, in case of electrolyte, they have quite high ionic conductivity. In case of electrolyte, they have quite good catalytic properties. So I will briefly go about their properties. Here we have a high temperature accelerated diffraction of our nanocomposite electrolytes prepared through two different methods. One method is freeze-dried method, which is a Pecquenet method, and then we also have solid state method. And on the left side, we see the XRD of those. And these phases, these peaks, they are confirming that the synthesis is successful, and we get all the peaks of this doped ceria. So these peaks are matching. And this NLK, sodium lithium carbonates, are mostly basically are in amorphous phase at higher temperature. And we confirmed this by doing this XRD at high temperature. So these peaks are from this doped ceria. But here we have a tiny peaks in the 3D, we can see these are basically from these carbonates. And here we have the temperature axis. And we notice that above 350 or around 400 degree, these peaks are disappearing. So basically we have some crystalline structure of this carbonate phase, but above 400 degree, all the carbonates, they are in amorphous phase, and that's why we don't see any peak here. So this is confirming that something is happening to these carbonates at around 400 degree. In this slide, I'm presenting basically our TGA data, the thermogravimetric analysis, and here we have DSC. differential scanning calorimetry analysis. So our two samples, our two nanocomposite electrolytes, we heated them at 600 degree and slowly cooled down, and then we see that what kind of phase changes happens. And what we found is that around 373, they are forming this crystal. So this is the crystallization temperature, and this is the melting temperature of our nanocomposite electrolytes. So it shows that when the temperature goes above this temperature, these carbonates, they are in the molten phase. So there is a phase change. And that's one of the reasons that in our XRD, high temperature XRD, we see that the peaks from the carbonates, they are disappearing. And the reason is that our carbonates, they are melting and then they are in amorphous phase. Similarly, here we have this TGA data, and there we see that samples that we prepare from solid state method, we see different peaks. For example, the peaks around 100 degrees, they are basically from physically absorbed water. When we heat, we get rid of this physically absorbed water. So this weight loss is detected in terms of these peaks. So these are the different derivatives of this weight loss. Then there is a peak around 200, and that's basically coming from chemically absorbed water. And then we have also some peaks over 200. And we think that they are basically some removal of carbonates. The structures are not very stable, and we lose some carbonate above 200 degree. But if we look at the other sample, the freeze-dried sample, we have peaks below 200, which are due to this physically absorbed water. At 200, we have this chemically absorbed water, but afterwards we don't see any loss of weight. So it shows that apparently that the nanocomposite electrolytes that we prepared from freeze-dried method, they are very stable and there is no weight loss. So we tried this 3D tomography and on our nanocomposite materials prepared through this freeze-dried method. So here you see the clusters of these nanoparticles, and the colors basically tell about their density, the surface densities. And here we see the clusters of these nanoparticles. The size of these clusters are about 200 nanometer, and there we see that the particles are of different size. And if you give it a closer look here, we see that they have quite surface properties they have different surface densities. And these actually help in the ionic conduction when we have different interface of this carbonates and oxide phase. So they play a major role in the ionic conduction. And here we have scanning electron microscopic images of our nanocomposite electrolyte pellets in the fuel cell. And what we see is that in this image, we can see that these electrolytes are very dense. This is a very important property of an electrolyte, because if an electrolyte is dense, we ensure that when we supply gases on both sides of the fuel cell, there is no gas crossover. Because if our electrolytes are porous, then there is a danger that our gases are crossing over through the electrolyte, and then which is not good for fuel cell performance. So our electrolytes are quite dense, as we can see from this scanning electron image. And if we give a bit closer look, we see that there are two phases inside. We have some crystalline oxide phase, and then we have this amorphous phase. And basically, it's like a core shell structure, and their interface is basically is the key behind this improved ionic conduction. So the oxide phase basically look like some stones, and this amorphous phase, it look like sand. So it look like a combination of sands and stones. So we have these two different amorphous and crystalline phase. But in addition to that, we also see some fiber-like structures in our electrolytes. So these fiber-like structures are basically due to the presence of hydroxides. They can be alkali hydroxides, or they can be hydrogen, basically water inside our fuel cell materials. So these are basically these hydroxides inside. And since our nanocomposite electrolytes also conduct hydroxides, so we see these fiber-like structures. Here also we see these fibers. And here we have, you can see that this amorphous phase and this crystalline phase, and then we see also these kind of holes. And we assume that these are probably due to this evaporation of this carbonate phase, and we see these kind of holes also. But these are very tiny in size and very few. so it doesn't lead to any gas crossover. And if we look at these nanoparticles of our oxide phase, from there we can see that the average size of these oxides is about 50 to 60 nanometer. And using this nanocomposites, especially from this freeze-dried method, we achieved a record high ionic conductivity. So our nanocomposite electrolytes, they give about 0.5 Siemens per centimeter at 550, and this is the world record performance of these nanocomposite electrolytes. And using these nanocomposite electrolytes in our fuel cells, we achieved about 1.1 watt per square centimeter at 550, which is quite high performance. And we published lots of papers on this, but especially this breakthrough was published in this Materials Today Energy, and it got attention of this fuel cell community because we get really high ionic conductivities of our electrolytes and quite good performance of a fuel cell. So this is like published in news. And here in this slide, I try to benchmark the performance of our fuel cell with one of the best results reported in the literature. And if you look at this, one of the best results reported in the literature by Professor Lee et al., we see that the total thickness of their cell is about 120 micrometer. And more specifically, if you look at the electrolyte, it's only 9 micrometer thick. In our case, our cell is 600 micrometer thick, about 5 times larger in thickness. And our electrolyte is also about 300 micrometer as compared to 9 micrometer. However, when we look at the ionic conductivity of their electrolytes, we see that it's actually orders of magnitude lower than our nanocomposite electrolyte. So the reason we are having lower performance is mainly because our cell is too thick and we have more ohmic losses. So if we can reduce the thickness of our electrolyte to, let's say, 9 micrometer, then we envision performances beyond state of the art. So this, we are using our materials, we can easily achieve performances beyond 2 watt per square centimeter, which will be really the top results in the world. So to achieve this, we have to also think about the fabrication method through which we are manufacturing our fuel cells. So the conventional methods are basically based on these pressing methods, and there are certain limitations because using these conventional pressing methods, it's very difficult to control the thickness of our electrolyte layers, and it's very difficult to control thicknesses below 500 micrometer. So although we have achieved about 1.1 watt per square centimeter at 550, and but somehow it's so difficult to reduce the thicknesses and achieve higher performances. And the best results reported in the literature, they were using these conventional printing methods. It's screen printing method, tape casting, and we're using these printing methods. You can achieve like thinner layers, and you have lower ohmic losses. So now, from last years, like in my academy project, we are focusing on digital printing, and the idea is to use our nanocomposite materials and we synthesize those. We prepare our fuel cells using printing methods, and especially we are focusing on digital printing, which are inkjet printing and 3D printing. So, for instance, here you see that these are our 3D printed fuel cells, and what we are at the moment, and we are achieving quite high ionic conductivities, and with reduced thicknesses, we are expecting that we will achieve performances about like over 2 watt per square centimeter. So this is our key research area which we are focusing on these days. So another issues that we are working in our lab is basically about their stability. We are quite experts in studying degradations in different electrochemical devices. And for instance, what we noticed in this specific kind of fuel cells are that their performances was decreasing gradually as a function of time. Like from 700 day goes to 600 over a span of 200-hour test. And the reason for their degradation was the interface between electrolyte and electrodes. It was not very stable. And some of the elements in electrodes, they are diffusing into the electrolyte at high temperature. And nowadays we are working on these blocking layers using this PLD or ALD atomic layer deposition techniques at the interface between electrodes and electrolyte. And now we are getting improved results and more stable results. Okay, so that was the first part of my presentation, and now I will switch to like single layer fuel cell research. So the first question is, what is a single layer fuel cell? So like any electrochemical device, a fuel cell usually basically have three layers: anode, cathode, and electrolyte. But unlike these conventional fuel cells, single layer fuel cell have just one layer. And the single layer, which is basically a combination of homogeneous layer of ionic conductor and catalyst material. And this layer offers all the electrode reactions and the ionic conductivity. So all the processes that takes place in these three layers, now all the three processes are taking place in just a single layer. But the fundamental question comes in our mind that why this cell is not short circuiting, because we have only one layer. And if we have electrons on like both sides, why it shouldn't like it short circuit? So that's the fundamental question we have with this single layer fuel cell technology. But surprisingly, these fuel cells work, and not only work, but they work actually they give quite high performances. For example, in literature, we have found a wide range of performances from 200 to 1 watt per square centimeter at 550. So at very low temperature, they can give really high performances. And this kind of structure gives some additional benefits. For example, when we have to fabricate our conventional fuel cells, we have to have three layers. And when we reduce it to single layer, it reduces our manufacturing cost. So now we have to just print one layer, and that's basically our fuel cell. So it reduces our manufacturing cost. Also, we have found that when we switch the gases, for example, in conventional fuel cells, you have to supply fuel always on the anode side and air on the cathode side, or any oxidant on the cathode side. But in case of single layer fuel cells, if you can switch the gases, if you can supply fuel from here and air or oxygen from the other side, it still works. It just changes its polarity. So this kind of system really simplified the system design. So we don't need to worry about like all the connections there. So it really simplified the system. Furthermore, it improved the thermal stability. For example, in case of conventional fuel cells, when we have three layers, these materials have different thermal expansion coefficients. And at high temperature, the interfaces, we have these thermal stresses that can cause cracking of the cells. But in case of a single layer, we don't see these kind of problems. And as a result, these cells have improved thermal stability. But the fundamental question is why these cells are not short circuiting, how they are actually working. And for that, in the literature and in our studies also, there are different speculations made on its working mechanism. And some of those speculations are based on this p-n junction, that since these materials, they used these semiconductor materials, n-type and p-type semiconductor materials, and when we supply gases, there's a p-n junction formed in the fuel cells. And the built-in voltage of these junctions, they prevent the short circuiting. Similarly, in some other papers, another speculation was made that basically it's a Schottky junction, because when we supply hydrogen on the anode side or one side of the cell, basically all the metal oxides, they are reduced to metals, and these metals and semiconductors, they form a Schottky junction. And these Schottky junctions basically prevent short circuiting of the fuel cell. Similarly, the working mechanism has been explained with bulk heterojunction concept. Like that's so that's also one speculation. And another speculation is based on that since these materials are using wide bandgap semiconductor materials, so maybe they have enough high electrical resistance that still prevent the short circuiting of the cell. So these are different speculations, and what we did is like we try to systematically study the working mechanism of these fuel cells and try to find out like what are the dominant ionic conductions happening in these cells. So for that, we use two promising nanocomposite materials for single layer applications. So first is based on lithium nickel zinc oxide. So this is the catalyst and our electrode material. And then we have this doped cilia, which is the ionic conductor. So these cells are basically these black colors cells. These are single layers, and this is how they look like. Then we also made some single layer fuel cells based on another material, basically nickel free material. And that's basically copper iron oxide. and which is basically a catalyst material or electrode material. And then we have this doped area, which is the ionic conductor. And these cells look like this, a bit like brownish color. Here's the schematic structure of the single layer cells, a single layer homogeneous mixture of ionic and electronic conductors. And what happened here is like we supply hydrogen on one side and oxygen or air on the other side. And as a result, we get hydrogen ions or oxygen ions, which moves in the opposite direction. And again, the only byproduct is water. And now we are trying to study these two nanocomposite single layer fuel cells and try to understand their mechanisms. So first, we try to optimize the sintering temperature for their fabrication. When we are fabricating these fuel cells, we need to sinter them, because the sintering gives them basically different physical properties, but also strengthening their mechanical strength. So for example, what we noticed in this case of copper iron oxide, so here is the XRD at different temperatures. And what we found is when we are increasing temperature, the size of these particles, they are basically increasing, and the surface area is basically decreasing. And for example, here is 7.4 nanometer, and when we center these pellets at 1000 degree, it increased a lot. So using these methods, we can control, like sintering method, we can control their size of the particles. So basically that's one thing. And when we measure their electrochemical properties, what we found is the cells which were sintered at 700 degrees, they give the most optimal performances. And so from these, we concluded that the 700 is the best temperature for these specific single layer fuel cells, because the main challenge in single layer fuel cell is that basically for its electrolyte function, it has to be very dense, but to function as electrode, it should be porous. So we have to make a compromise between its porosity, because if it's too dense, then the cell performance is limited. For example, in this case, the cell performance is limited because we don't have enough surface area for the electrode reactions. But if the pellet is very dense, then we are limited by the electrode reactions. But if the electrolyte is porous, then it affects the ionic conductivity, and the cell performance is limited by the ionic conductivity. So that's kind of a compromise between the two, and apparently 700 degrees gives the best result for these specific materials. And here we have results for the other lithium, nickel, zinc, doped area. So this is as transmission, high resolution transmission electron images, and there what we see is, or we can already see these crystal planes here, these atoms here, and what we see is the lattice constant about. So these are the distances between these atoms, the spacing, and these are actually matching quite well with the d-spacing we get from this XRD data. And these materials have quite wide bandgap materials, like 3.6 electron volts. And there we apply different current collectors. So we have the single layer composites, and there we apply different current collectors. In this case, we have gold. But in most of the single layer literature, mostly researchers have been applying this NCAL coated nickel foam, and NCAL stands for nickel, cobalt, aluminum, lithium oxide, and nickel, and they are used for this current collection. But we were thinking that maybe these are actually quite frequently used as an electrode material in batteries. So we were suspecting that they are improving the electrochemical performances, and they are not just acting as current collector. So this kind of configuration we cannot call a single layer fuel cell, because these are actually acting as electrodes. And in order to verify, we prepared some samples with gold as current collectors, because gold is quite inert, and so it just helps in the current collections, not in like any like fuel oxidation. And what we found here is like when we are using this NCAL coated nickel foams on both sides of the cells, cell performance is almost doubles as compared to cells where we don't have this NCAL coated nickel foams. So that confirms us that this NCAL improves the electrochemical performances through this catalysis. And so this kind of configuration is kind of a conventional three-layered structure. But this is definitely single layer cells, because this is the only functional layer here, and it gives quite high performances. So that shows that the single layer fuel cell definitely works. and it's like the performances are still quite high. But how it works, we try to figure out in a systematic study. What we did here is that we prepare our cells with different thicknesses. We prepare this lithium nickel zinc doped celia cells with thicknesses of 1 millimeter, 2 millimeter, and 3 millimeter. And we measured their electrochemical performances in different gas atmospheres. For example, in the first case, where we have this nitrogen on one side and air on the other side, we see that the cell resistance is quite high. For 1 millimeter, it's about 3.35 ohms square centimeter, and it goes over 104 for 3 millimeter. But when we supply hydrogen on one side and nitrogen on the other side, the resistance goes dramatically reduces to 1.17 ohms per square centimeter for 1 millimeter thickness. So basically, in this first case, it's only oxygen ions which can conduct in the cell, because this nitrogen is quite inert, and oxygen ions, basically air can only give oxygen ions in the cell. So there is only oxygen ion conduction taking place. But in this particular case, we have hydrogen ions which are transporting in the electrolytes. And we see that the cell resistance has gone down dramatically. When we supply both hydrogen and air on both sides of the cells, we see that the cell resistance is reduced even further. And that shows that in this specific case, apparently both hydrogen conduction and oxygen ion conduction is taking place. And the cell resistance reduces even further to 1.07 ohm per square centimeter. And even the 3 millimeter thick cell gives resistance about 3.51 ohm square centimeter. And we also checked with this electrochemical impedance spectroscopy. And for example, for this specific sample, we see that the cell resistance is going down when we are decreasing the cell thickness. So here we see this inductance, and this gives the ohmic resistance, and the semicircle here that we see, that basically gives us about the electrode resistance, the polarization losses in the cells. So based on these comparative analysis, what we found is that it's hydrogen ion which is dominating the conduction in this specific kind of fuel cells. Then we try to study some other performance limiting factors. For example, here we have conventional single layer fuel cell, this doped celia, gadolinium doped celia, plus lithium nickel zinc oxide, and we have this gold layer on both sides, quite dense layer, and we get about 220 milliwatt per square centimeter. In this cell, we added some porous layers of the same material. So these porous layers are the same GDC plus LNZ, but we added some pores there so that we can improve the electrode reactions. So we have these porous layers, and what we found is the cell performance improved by 30% when we add these pores. So it shows that in this dense layer, the cell resistance was limited by these pores, by the electrode processes. But by adding this kind of porous structures, we can improve the cell performances. So the cell performance is improved by 30%. But we can do further optimization, and we can improve the cell performance even further. In this particular case, we have different kind of ionic conductors. For example, here we have this GDC, which is basically a good ionic conductor, but it has relatively lower ionic conductivity because it's only oxygen ion which is conducting in the electrolyte. And in the right side, we use really high ionic conductivity, one of the best that we have. And what we found is the cell resistance almost doubles. The cell performance almost doubles when we use really high ionic conductivity materials. And that shows that by using different performance parameters, ionic conductivity, and adding pore structures on both sides of the cells, we can improve the performance of the single layer cells. So basically that was about our performance limiting factors in single layer fuel cells. And now I will briefly talk about like our key conclusions based on the two technologies that I presented. So basically in our research, we have achieved 1 watt per square centimeter milestone, but that milestone is achieved using conventional powder press method. The problem with that technology is we cannot upscale it because we have to apply lots of pressure on our on our powders to make these kind of fuel cells. So when we go for upscaling, it requires a lot of load to create such a high pressure to make those kind of fuel cells using this powder press method. So in order to upscale and also to improve the performances, because our cell performances are limited due to their thicknesses, and that thickness problems come from this powder press method because it's so difficult to reduce thicknesses by powder press method. So now we are focusing on digital printing methods, and that's solving basically two problems. First, using these digital printing methods, we can control the interfaces and the thicknesses of our fuel cell layers, and by using those and using our promising nanocomposite materials, we can achieve performances above 2 watt per square centimeter. In addition, using these digital printing methods, they are upscalable. We can make cells of larger sizes, and easily we can go for like large scale production of our fuel cells. And this production line using this 3D printing and this inkjet printing, so it's also low cost technologies. So it can significantly reduce the cost of these fuel cell technologies. Third is like in order to achieve that, you need to have inks of all those promising nanocomposite materials, which is a challenge because in our materials we have different phases, and it's a big challenge to make inks and paste of those materials. So nowadays we are focusing on developing inks of our this robust nanocomposite materials. And also, we are studying different performance limiting factors, ionic transport, the transport number of these ions in our electrolytes, catalysis, reaction kinetics. So we are focusing both on the modeling and also doing the experimental work and trying to develop our understanding on this topic and try to remove these performance limiting factors and improve the fuel cell performances. And the most importantly, this is an excellent technology, and in order to commercialize, and we need to improve its stability. And for that, we need to understand degradation mechanisms. So what we are doing in our group is like we are systematically studying different degradation mechanisms, and we are developing materials and processes to overcome all these degradation mechanisms. So these are overview of our research activities. And before I finish my presentation, I would like to briefly tell about like admissions in Finland for master's program. Finland is a beautiful country, offers quite high quality education. And these links, you can find more information about admissions in Finland. And the good thing is like they offer lots of scholarships, 100% scholarships to cover all the tuition fee. And the admissions they're open now from 1st of November to the end of January. And please go through these links if you're interested to study in Finland. So this is our university actually these days. So we have some snow here, and so that's the Aalto University building. So with that, I'd like to thank you for your attention, and I will be very happy if you have any questions. So thank you very much.
Thank you very much, sir, for your nice presentation. And I request participants ask the question. If you have any doubt, query, ask the sir.
Sir, there are two questions in question and answers. One is how the cell resistance has been measured. This is one question. And the second question is, have you estimated the electronic transport effect on the cell performance?
Yes. So basically, we measure the electrical resistance or the impedance through the cell using two different methods. So we have basically this electrochemical impedance spectroscopy. That's one main method that we are using. And the good thing about this electrochemical impedance spectroscopy is that we can not only see the total resistance of the cell, but we can also see the resistances or the impedances at different interfaces in the fuel cell. So electrochemical impedance spectroscopy is the main technique that we use. But also from these current voltage curves, we can estimate the resistance of the cell. So these are basically for the resistance. And the second question was about this electronic resistance. So basically, we try to do this systematic approach. So first, we always measure our fuel cells in nitrogen atmosphere. So when we do measurements in nitrogen atmospheres, so basically there is no redox reactions happening. And the only conduction that is happening through our cells is the electronic conduction. So from doing this impedance spectroscopy and the IV measure current voltage measurements in nitrogen atmosphere, we get the electronic conductivity of our materials. And then by applying different gas atmospheres, we can create different redox reactions like oxygen ions or hydrogen ions, and then we measure their ionic conduction. And we have also been working on this EMF method. So we have a quite nice equipment where we can change the partial pressure of those gases, and we can measure the ionic transport numbers of these ionic conductions. So that's how we measure the ionic transport. And for electrons, it's basically measurements under nitrogen atmosphere through electrochemical impedance spectroscopy and current voltage measurements. I hope it answers your question.
Another question? Kage sir, is there another question?
No, nobody has raised hand, I think.
Okay.
Yeah.
Okay, thank you, sir, for being part
Thank
of
you
this
very much.
conference and your nice lecture and talk. So, thank you very much again.
Thank you very much. Thank you.
Kage sir. Kage sir, continue.
Yes, sir. Yes, sir.
Okay, okay, okay. Now, the next session. So, welcome you again in the next session of this conference. So, for this session also, we have an eminent personality and scientist, Professor S.S. Prabhu. Professor Prabhu did his PhD from Tata Institute of Fundamental Research Center, Mumbai, and recently he is working as associate professor in physics. He has more than 52 papers in international journals and more than 80 papers in conferences and has given several invited talks. His research interests are ultra-fast time-resolved phenomena in materials spectroscopy, metamaterials, high-field terahertz and near-field terahertz microscopy. Today, he is talking about the challenges and future trends in terahertz spectroscopy. And we have such eminent personality, so I request you, sir, to deliver the talk. Professor Prabhu, sir.
Okay, good morning, all of you. And thank you, Professor Gedam, for such a kind and nice introduction. I hope I will stand by what you have said. You have been very kind. And I also wish to thank Dr. Ishwar and Dr. Vishal Panse. I met him quite long years ago, but it's very nice of all of you who have remembered me and also giving me this opportunity and inviting for this nice conference. It's a very nice, organized conference, and I hope I will give you some flavor of what kind of work that and so basically today I will speak about the challenges and future trends in the terahertz spectroscopy. So I am from TIFR, so I'll tell you a little bit more about that. Before that, I will just talk about the overall plan of my talk. So I will talk about what this terahertz is all about, what are its advantages, limitations. Then I will also talk about the terahertz sources and detectors which we have developed indigenously. And then there are various designs of these sources. We will brief in a little bit, and then we'll talk about detectors and spectroscopy setups that we have developed in India, all indigenously. A little bit of data analysis and then outlook at future directions. So first, let me take you for the terahertz through a journey through time. And you can see that this terahertz, which is basically new field since 1980s, you can see the number of papers, and they have been growing exponentially large. and if you plot them on the logarithmic scale with base 2, and you can start seeing that it's almost like a straight line. And if you try to fit some curve to it, you see that it is doubling every 3 years. So this continues to grow, and these terahertz and terahertz gap, these words, they keep appearing in papers, and they are continuously growing. So it's a very hot field, and a lot of applications are there, and you will really see why I'm saying this is hot field and why so many applications are there. So typically terahertz gap is defined by various people. I mean, they define it right from 0.1 to like 10 terahertz, or sometimes they define it from 0.3 to 10 terahertz, or from 0.3 to 30 terahertz. So the latest one is roughly like 0.1 to 20 terahertz. So you can take it basically 100 gigahertz to 30,000 gigahertz band. That is the kind of band that we are looking at. And what is so special about this? So now these journals have come up. So one is Journal of Infrared Millimeter and Terahertz, which has been going on since 1980s, and is a new journal last 10 years. It has come up. This is Terahertz Science and Technology. So their impact factors are also going up. The biggest conference through this is the Terahertz conference. In 2004, they merged it with the infrared and millimeter wave, and this is the conference where from all over the world, whoever is working in terahertz, in technology, engineering, or development and science, and there everybody attends this. So the last 2 years that it was in 2019 it was in Paris. Before that it was in Japan. So this year, because of this pandemic, it was held virtually, but it was supposed to be at Buffalo, New York. From November 8 to 13 it was held, all virtual. Next year it will be probably partially virtual and partially physical in Chengdu, China, August 29 to 3. So you can remember these dates. And then next year after that is in Rotterdam, Netherlands, September 4th to 9th, and after that it is again in Canada. So you can see that it actually circulates between Asia, then Europe, and then in American continent. So all these three, it is cycled. In 2024 it should be in Asia. So let's say I wanted to actually bid for it, but most likely will probably bid for 2027. There have been a lot of books which have been written through times, and the latest book in 2019 is on the principles of terahertz time domain spectroscopy. I'll also speak about that. And you can see slowly a lot of this literature is coming up in these books. So where is this terahertz? Basically, this is the electromagnetic wave. All these different frequencies, and you are all familiar with the gigahertz, where it lies this region. Your computers and other devices work in that. However, the visible X-ray, gamma ray, they are all in the higher frequency. So visible is coming to like 10 raised to 15 or so. So terahertz lies exactly between these two. So in terms of wavelength, if you see, 1 terahertz is like 300 micron wavelength, which is quite large compared to the visible one. Visible one is like 0.4 to 0.7 micron, or 400 to 700 nanometers. So it is much smaller than this. So this is also called a far infrared. So this is basically 1 picosecond cycle, or the photon energy of this is like 4.1 milli-electron volt. And those of you who are familiar with Raman and this type of things, the wave numbers, this is like 33 wave number, like 1 terahertz. And 47.6 Kelvin is the energy of this photon. So you can see, if you want to detect this photon, you need to have detectors which are cooled down to below 47. So that means roughly liquid helium temperature only it will work. It is very rich science, but very poor technology. So a lot of work is going on. A lot of agencies are interested. So Europe, America, they have put in like billions of dollars and euros for these kind of projects. And they are trying to get applications in sensing, imaging, inspection, medical, defense, law enforcement, communication. So communication probably is the closest one to us, because right now we have 4G, people are going for 5G and 6G. The 6G will be falling into the sub-terahertz region. Now, what are the advantages of this? So you can see that there is a photograph of this person who is carrying this newspaper, but there is a weapon which is he's carrying a dagger, and it is hidden behind this newspaper. And you can see that the terahertz penetrates through the clothes and also the paper, so you can see what else he is carrying, and this is very clearly visible because of metal. And this is the photograph of the tooth. You can see the enamel and other things. And these are all these spectra very specific to different kinds of explosives or molecules like RDX, HMX, PE, and TNT. So these are very unique molecular spectra, very unique to these molecules. So you can do what is known as frequency fingerprinting and identify these materials if any of these people are carrying. So what are these advantages? So large number of these molecules have rotational vibration energy levels in this terahertz range. So that's why they can be very uniquely identified if somebody carries that. And the second advantage is terahertz passes through opaque materials which are otherwise opaque to the visible or optical beams. So you can actually see what the person is carrying inside. Terahertz is very sensitive to water, so it cannot penetrate through our body or skin. So only peripheral skin only you can study. It cannot go so inside. So that way it is quite safe. So you can basically scan a person and see what he is carrying inside. So there are also some privacy issues because of that at the airports and other things. But definitely, if somebody is hiding something, they can be detected using this. One is very much interested in this high intensity terahertz radiation, because that way you can identify people, somebody carrying something, say 100 meters away, you can immediately neutralize that person is carrying anything. So this way it is very useful radiation. And main problem is, as I told you, the water absorbs terahertz very heavily. So therefore, terahertz really can't travel too much in air. And therefore, all the experimental things that we have, setups we have, they are all kept inside this nitrogen purged boxes. So you will see all our setups are inside nitrogen purged boxes. So we cannot have even a little bit of water vapor. Otherwise, it completely attenuates the error. So the kind of powers that we have been able to generate in our laboratories are in like pico, nano, or microwatt. So they are well, and therefore all over the world there is a big race going on to increase these intensities of terahertz. And also you want to have something, the detectors which can work at room temperature, because at room temperature KBT itself is 26 way above 4 milli electron volt energy of the terahertz photon. So it is a huge thermal diagram. So here I have actually listed all the different sources, and you can see as a function of frequency, suddenly there is a huge fall as we approach 1 to 3 terahertz region. And the only sources which are very high power available in this region have to be operated at very low temperatures like liquid nitrogen or liquid helium temperature. All they have to be something like quantum cascade lasers, but again they have to be also operated at low temperatures. Or you have very high power which are like free electron lasers, but those require synchrotron kind of thing. So synchrotron, already that is few acre big machines, and that way you need an accelerator. So again, it is not a very practical solution. So what we do is right now, I will talk in this talk is about this photoconducting antenna, which is at the bottom part. But you can see that we can, although the power is quite low, several orders of magnitude, we are trying to increase this somehow. And in TIFR, we have done some part of imaging of these leaves, and because I told you these are familiar, they are very sensitive to water lines. You can see that the leaf has a very less water at the edge, and wherever there is a lot of water, you can see this dark portions here, and the same thing here. Same thing we did for the watermark also. For this is a old 500 rupee note, and you can see Mahatma Gandhiji's photograph can come out, although it is not directly visible. So this is basically because of the density variation. So the basic idea is we need very sensitive broadband, room temperature operable, high dynamic range, reasonably priced detectors, as well as high widely tunable and reasonably priced room temperature operable sources, high power sources. We also need, if they are broadband, they can be, they can go up to say 10 terahertz or 20 terahertz. Great. And the important thing is one can do long range imaging like more than 25-meter away. That would be a great thing to have terahertz cameras for good performance. So in our laboratory, we have photoconducting antenna which generates large power. We have electro-optic crystals for rectification, and we also have photo mixers in-house developed which are used for CW terahertz. We also have in-house built bolometer which operates at about 1.8K. And again, photoconductive dipole antennas and electro-optic for the detection. These are actually made for all these experiments. So the basic principle of terahertz generation is using the optical rectification. So one can put the laser pulse that has certain width and certain time pulse. So this is roughly 100 femtosecond to 10 femtosecond. So that generates polarization in the crystal, and what happens is rate of change of this polarization is proportional to the electric field. Now what happens is you are basically now limited by the bandwidth of the pulse. So you can see here, this is the bandwidth of the pulse, delta omega, and larger it is, that means shorter the time, and then would have much broader terahertz generation. So this is what you can actually detect terahertz as a function of time in picoseconds, and then the Fourier transform of that will give you the spectrum of the sample. So I will talk about that a little bit later. So first let us concentrate on the photoconducting terahertz sources that we made. The basic principle is that you put an incident photon of say 800 nanometer and 10 femtosecond kind of height. You generate electron hole pairs in the device, and then you apply an electric field. So once you apply an electric field, you are going to accelerate these electron and hole pairs, and they will basically generate this electron pulse, which is the terahertz. Now what we do is we take this semi-insulating gallium arsenide, then we put these two electrodes over it, and then we put this incident pulse which is about 10 to 100 femtosecond, and then you have these two electrodes which are biased with plus and minus, and then you accelerate this terahertz in this path that generates this terahertz. So this is how our actual device looks. So you can see that it is quite compact, and this is basically, it generates this current pulse, and the rate of change of this current pulse is the one which is emitted as a terahertz pulse. So these are the different factors that it is dependent on, and we will see how we can modify these step by step. And these are of the following type. So one is that you can either modify the entire bulk, you can also modify these electrodes, their arrangement, their designs, etc. And in the end, you can also modify the surface which is between these two. So we will go step by step, and we'll show you how we have achieved it. The most important material that is required as a substrate is the low temperature gallium arsenide, because it has a very low carrier lifetime. However, it is banned for sale to India, so we could not procure it. So therefore, we bought this CR-doped semi-insulating gallium arsenide available in open market, but that has a carrier lifetime of 50 to 100 picosecond. That is quite large, but it has very good mobility and other parameters are matching. So what we did is we used this, and we artificially created defects in it using the Pelletron machine or accelerator machine is available in TIFR. And using that, we were actually able to make these devices, and you can see that the implanted one showed very low dark current, and when we excited it with the carrier, some excitation of 125 milliwatt or so, even the current that was drawn was 2 orders lesser than the current that was drawn from the sample without implantation. So you can see that right here itself, we have gained 2 orders of magnitude lower current. And in terms of the terahertz radiation emission, you can see that this black curve is showing you the arrow where our device, semi-insulating gallium arsenide, which was not implanted, got destroyed, while all the other with different implantation dosages continue to give a huge amount of emission, and we could actually generate almost 100 times higher intensity terahertz radiation using these, and these resources became quite robust. Then you can, so this way we actually had modified the bulb. Now you can also modify the electrode designs. So one can have an interdigitated design, and that interdigitated design means you can have these devices, just like fingers that you see my hand, and the fingers. I mean, this is how you can have them and excite this entire region. And if you do that, you will basically generate almost 10 to 100 times power. You can also have what is known as a plasmonic design. That means this entire surface that you are seeing right now is a plane surface. If you can modify its properties so that you make them interdigitated, but at the same time, each of these I mean, instead of plane, you make it just like the comb that you use for combing your hair. So in that case, it becomes a completely different, its properties change completely. So what happens is when you have this type of surface or the design, these are of course done using E-beam lithography, and the separation between these two small units is almost 200 nanometers or 0.2 micron, which is 1/4 the wavelength of the light incident on it. So what this does is basically the 800 nanometer light which is falling on it does not see this as a normal dielectric or a metal. It just sees it as some completely different kind of dielectric. And if its polarization is horizontal, then it goes through, while if polarization is parallel to these small electrodes, then it gets reflected. So this becomes polarization dependent. And we found that if you have this type of electrode, and if you input this 800 nanometer proper polarized light or incident on it, we get almost 10 times higher generation of terahertz from this region. While if there is a plane part, then you get only the same kind of generation, say 1 times. So now you watch this, here you will have 10 times higher generation, but the electric field is going in the up direction, while here the field is in the opposite direction, down electric field. So this here the electric field will be generated with terahertz will be generated, but it will have polarization, which is electric field which is going in the opposite direction. So these kind of things can cancel each other. So this efficiency of this device will be less, while here this is going to be plus 10 minus 1 plus 10 minus 1. So overall, without using any kind of small or micro lenses, you can use full light beam and utilize this to generate huge amount of terahertz. And this is what we did. You can see that there's a huge polarization dependence for horizontal and vertical polarization. You can see that there is a huge change in the terms of current as well as in terms of the terahertz. And this device, which we call it AP-IPCM, it is anti-symmetric plasmonic interdigitated photoconducting antenna. You can see that it actually can go and work beyond 200 milliwatt, and that was the highest power that we could put in, but it can also work up to 500 watt. So this could generate a huge amount of power. So this way we showed that it could improve on these. Then you can also modify the length. That means if you just have this electrode, this is a cross section. So if you just have a simple electrode, you will see that it is only going horizontally, and the carriers will be generated just below this. But if you etch this surface and make these kind of periodic structures, now you can generate carriers after excitation into these three-dimensional part, and these large number of carriers which get generated would also improve upon you. So This gave us an idea that we actually also modify the surface in between and do it. So for this we had to do a lot of these simulations with different kind of structures, circular, horizontal, triangular, hexagonal, square, all kinds of things. So here the basic idea is you have a dielectric, which is basically the semi-insulating gallium arsenide, and air, which is basically the gap that is being shown here. So this way you can modify the surface properties and try to get maximum amount of 800 nanometer that is incident on it coupled to the surface. So this is the actual device. This is the AFM of the pattern made, and this is how our device looks. And this is the actual photograph of our device, and you can see that this region is excited, while this region is the one where there is no pattern. So we have these two devices right next to each other, so there is no question of any variations. That's how we compared them, and you could see that the bias. This is the bias direction, which is parallel, and the polarization of the incident light. If you change it, I mean, you can either have it parallel to the bias field or perpendicular to the bias field. We thought there would be a difference, but actually we found the same current. So we were a little bit surprised that why this happened. But always remember that the terahertz is a time phenomenon. So when we saw actually the terahertz emission from this, the parallel, uh, you know, electric field gave us much higher terahertz than the perpendicular one. And the reason for this was we of course did of simulations, which I will not show it here. Give a quick idea. So if we when we did the simulation, theoretical simulation, we found that the whole structure when you have polarization parallel to the bias field, it generates all these hotspots in between these, and the carriers get accelerated, but they get immediately captured by these defects, and as a result, you generate high terahertz in here. While here, the carriers will move without getting scattered. So as a result, your current is flowing very beautifully, and there is really no current pulse. So that will actually reduce the terahertz. So with the surface modification, we could actually show that we are able to generate quite a bit of terahertz. Then we also tried these samples for this CW, that is continuous wave terahertz radiation. So this is the device that we made, and this is the ACM of that. And you can see that the basic idea is you take two CW lasers, you put them, focus them in the center here, in this region. And here, basically, what you do is you have a sine, say, you just look at it like a sine of omega 1t and sine of omega 2t. So you mix these two. So that will generate basically omega 1 plus omega 2 and omega 1 minus omega 2 kind of wavelength frequencies. And then omega 1 minus omega 2 is the one which is this envelope, which is a slowly varying envelope that is in the terahertz. And so this is basically this carrier grating, which is changing in time. So it's like an AC current of the terahertz frequency, which is you are feeding to this entire antenna, and that emits the signal frequency. So you could see that our implanted samples showed pretty large up to 1200 gigahertz or 1.2 terahertz, while the semi-insulating one, which was not implanted or which had a long carrier lifetime, actually saturated way deep. So we also made these photoconducting antenna detectors. So basically the idea is the same. Instead of biasing these two electrodes, now you just measure current across. But how will the current flow? There is no electric field. And where are the carriers? So to generate carriers, you have this pulse. But to generate the electric field, you basically put the terahertz field. And now you see the positive going field when it comes here, the current will flow in one direction. And if it is in the opposite negative part, the current will flow in the opposite direction. So you basically measure the current and its direction, and then that's it. So based on this, you have direct sampling detector or integrating ones. So we will only talk here about the direct sampling one, where the tau or the carrier lifetime is much shorter. So in that case, the current that you measure is a convolution integral of this. So the basic E terahertz, and this is the response of time. So if it is like delta function, then your current will actually exactly measure the. So what we did was we just did some modeling of this. and we measured this E terahertz using zinc telluride crystal, and that was the actual profile of the field. And then we made some measurements of time resolved reflectivity. So we have this time resolved reflectivity setup where we actually found out the carrier lifetimes of these different implanted samples, and then we used this and these two values in here, and numerically calculated these gray curves, and this was the actual current that was measured, and you could see that it matches pretty well. So this device also works pretty well. And now I will talk a little bit about how this terahertz pulse is there. So this is how you measure the terahertz pulse. So this is the terahertz pulse which is measured in open air. And then what you do is you basically put in the sample in the path of the beam and again pass terahertz through this. And because of the presence of sample, the terahertz pulse will be shifted in time and also gets attenuated in amplitude. So this actually tells you that there is a absorption as well as there is a proper refractive index of that particular sample. And using this information, you can do a lot of other things. So first thing that we do is we take the Fourier transform of these pulses, because this is in time. We need to go into frequency, and you can actually see the Fourier transform of this. And since it is done in open air, you can also see all these water vapor lines, and these are each one of these can be actually recorded, and you will be able to find the water vapor spectrum. And then when you put the sample will have its own spectrum, and you can see here that the sample is attenuating all the frequencies beyond 2 terahertz. So that's why when you divide these two, you will get a spectrum of the sample which is ending at about 2 terahertz. And additionally, this also gives you a phase information. So this way you can get the complete spectrum, as well as you have to modify the analysis a bit. So what you get is if you have a sample with two parallel surfaces, the electric field, when it passes through, it undergoes several different reflections. So accordingly, each of these surfaces will have their own Fresnel coefficient for the reflection as well as transmission, and then you can modify, you can model it together. And you take the refractive index not as a usual real part, but it is real as well as imaginary part. And if you take this, then you can also calculate what is the what do we call that as the um, dielectric constant, which is the full dielectric constant with real and imaginary part. From that, you can also calculate the real and imaginary part of the conductivity. So if you can do all of these together with this kind of analysis, so this is all we do. We also have developed some algorithms for that, programs for that. So using these, we actually take we can find out the N and K. So here I would like you to concentrate on this phi, which is the phase that we obtain when we take the Fourier transform. And this is the the imaginary part where we actually calculate this transmission coefficient, which is obtained from dividing these two amplitudes. And then you can calculate the N and K completely. And this is how the complete analysis goes. So first you pass terahertz wave through air, you take E terahertz, then you pass it through the substrate, then you calculate this complex refractive index of the substrate. Then if you have a thin film over it, then you again pass it through this, and now you can calculate the complex refractive index of thin film, because there are certain thin films like say metallic, they could be metallic, and then terahertz will get reflected completely, so nothing will pass through. So therefore you have to use this for thin film. So superconducting thin films, etc., can be studied using this. So we have done this study of this using this. There is a laboratory, solid state laboratory in Italy, and we use this semi-insulating gallium arsenide. You can see that it's pretty nice transmission you see. And why you see so many of these oscillations, because the two surfaces, there have been a lot of reflections which are taking place, which I mentioned to you here. You can see in this region that there are multiple reflections, and because of these you will actually see these Fabry-Perot oscillations in the frequency. So you can see also that there has been very low absorption for this semi-insulating gallium arsenide of terahertz, and one can actually do this. You can see this is done for, say, silicon wafer, some thick silicon wafer, and you can see that this is the pulse that is in the open air, and these are the ones which are in big circular pieces, and you can see because of the refractive index, the pulse has been shifted quite a bit. And you can actually take the Fourier transforms and basically get these spectra. And using that also you can figure out what is the refractive index. So the refractive index of these is around 3.45 or so, and we can and these oscillations again came because of the exact parallel surfaces of the silicon wafer, and we can actually do smoothing to basically remove it, and you can see this almost a constant refractive index, and this is also a very low K, less than 0.04. And although here it is going in the negative direction, is showing negative, that is because of this Fabry-Perot oscillation. So this is an artifact which you have to numerically remove it. So this also will tell you what are the kind of difficulties one faces doing this terahertz. So that's why it's a very difficult spectroscopy to do and do this analysis. So we have been also working on developing algorithms to remove some of these artifacts and try to get better models. So these are some of the models that one can use, by using this, calculating this epsilon dielectric constant. You can actually model it with several Lorentzian oscillators, etc. So we have done a lot of work on this, but of course there's not much time to speak about this. We also work on metamaterials. These are the materials which are artificially made. So we collaborate with Professor S.P. Dattagupta from IIT Mumbai and Professor A.V. Gopal from TIFR, with whom I also share my laboratory. And here we basically study these artificial structures. So you can, I'll just give you a quick glimpse of this, that you have this single bar, and if these two vertical bars are not present, the single bar will actually give you a spectrum with one dip, which is the resonant transmission dip. While if you additionally include these two bars, it actually generates a quadrupole, which you can see here, and this quadrupole will kill this horizontal absorption, and it will actually allow transmission of terahertz through this. So this is called electromagnetically induced transparency, which of some of you are maybe familiar with the nuclear ones. So we also make different types of terahertz filters, polarization filters. So you can see this is the simulated and the experimental ones. They can match pretty well. So these are cut wire metamaterial, which are actually polarizers, which are specific band polarizers. So they will work only in specific bands. So one can do such type of things. Now, currently, we are developing the first of its kind. It's called near field scanning terahertz microscope. It's the first time in Asia that we have this machine. It is again fully built DIFR house, and you can see that we have this the red beam, which again goes through. It's the same setup what we use for the terahertz generation. Now here the sample is put here, the terahertz passes through, and now our probe tip, it comes extremely close to the sample. For these spectra, all these spectra which I have shown here are measured far away from the sample. These are measured way away. So that's why these are called long field measurement, far field measurements. While here you can actually see these patterns, see these Dolman ones, where you are seeing these what I call the dipoles. These are numerically seen, but we would like to see this experimentally, and it was not possible till now. But now with this kind of design, it is possible, and it is done by this boy from Solapur. And here I am actually showing you this time evolution of this. This is the pattern, which is just a small square pattern of holes. Of course, this is microns. but you can see that there is a small pulse that is coming, and this is how, as a function of time, the pulses are coming out of this, and you will see these different modes which are coming out in picoseconds time. So you can see this, and its Fourier transform. If you see again, there is this portion where you have the whole and different frequencies are coming out. Now you can see the small frequencies are coming out first, and these are pretty large. And as the whole size is, you know, much, because of the periodicity and all that, the higher modes are getting destroyed, and you can see that they just vanish away. So this is the frequency evolution, and this is the time evolution that you can really study well. So these are the latest results that we have. We are of course analyzing this, and beyond certain frequencies you don't see anything. So you can see that higher frequencies are not present here. So although in time evolution you see different modes. So this is something that we are developing. So of course there are, I talked about all these photoconducting antennas and everything, but there are certain limitations due to incident intensity, multiple interdigited designs. There are several limitations of these, and low optical terahertz conversions, etc. But people are still working towards trying to increase this efficiency. So our current and future research basically will be in near field scanning terahertz microscope, one of its own kind in the country as well as in probably in Asia. So we also do work on terahertz waveguides, different fiber designs for detection of molecules, biomolecules. So this we also use it whispering gallery mode studies, etc. Although this is very limited time, so I didn't talk about any of these. We are also developing analysis algorithms for the terahertz data, which I showed you, because there are some issues still. So this is again still a hot topic. We also study new terahertz crystal for generation and detection. So you are welcome. You have linear crystals or electro-optic crystals you like to study. We are open for that. We also have this optical terahertz probe studies. This setup we are activating, and these are the other things that we are trying to activate, which is the material study under high terahertz field and as well as under magnetic field. And my dream would be to develop eventually this terahertz nanoscopy using STM like thing, because currently with this NSTM we can have resolution of 10 microns, with a wavelength of 300 microns, so which is 1/30th of the wavelength. That beats all the other diffraction limits. But STM can go into nanometers, so that is basically ultimate thing. So anyway, I wish to thank all these people with whom I had this association. These are all these students from different parts. So currently, this Ajinkya is working with me. He's from Solapur, and Prathamesh was from Parmani, Pune. These are other students are from Pune, and Abhishek is now he's in Dresden, Germany. Gajendra Mule is from Nagar. He's our scientific officer, and we wish to thank funding from the. These are all the other people who helped us at various times, especially Professor Doler also. I wish to thank him for a lot of interesting discussions that we had. And these are all the people who had been working. So now this is Gajendra Mule. He's from Nagar. I today talked about the work that was done by this Gautam and some Arnav and others. So these two worked on the whispering gallery mode. These two worked on different materials, and all these other ones are now abroad. So they work on different parts of this. So I wish to really thank all of them. I'll say also thanks to all of you, all the organizers, Dr. Panse, Dr. Ishwar, and many of you who actually could find time on Sunday to listen to me and are enthusiastically present here. And thanks, Dr. Geram, for very kind introduction. And I again thank all the organizers for inviting me. And if you have any of collaborative things, you are all. Thank you very much.
Thank you very much, Dr. Prabhu sir, for a nice talk, and hope everybody will be beneficiary for
Thank you, sir. Thank you very much.
thank you.
If there are any questions, please.
If there any question, if there any question. If there any question, you may ask to Prabhu sir.
They can also write to me if they are interested. There is no issue, because this is that way a little bit new field, and so I gave quite a bit of overview.
Sir, is there any question?
Sir, in chat box, I can't see any question. So I think there are no queries, sir.
Okay.
I think everybody liked, everybody understood what I said.
Yes, sir. Yes, sir.
So
Very nice lecture.
But thank you,
So
sir. Thank you.
very
And,
much.
Gadchiroli has been, I wanted to actually visit Gadchiroli sometime. Professor Atram, yesterday I saw him in was giving some talk, and I think he was chairing a session. So I had met him in TIFR. So it's a great pleasure. It would be a great pleasure meeting all of you. And thank you very much for organizing such a nice event. And I wish you all the best for your future such events also. So I hope that if the pandemic was there, I could have definitely visited you people.
Yeah, most welcome, sir. Anytime.
Yeah, thank you, Professor Gedam. Yeah, thank you so much.
Thank you, sir. Thank you very much. Thank you very much, sir. Dr. Kage sir, Dr. Vishal sir, and Dr. Sule sir, for giving me opportunity to present the session. Dr. Kage sir.
Yes, yes, sir. Thank you very much, sir.
Okay.
On behalf of Gondwana University and the CONIAPS 26 conference on advances on physics, I thank you uh, very much for chairing this session. Thank you very much, sir. Now we shall proceed for for next session. For next session, we have Dr. D.H. Gahane as a chairperson. Before proceeding to that, it is my pleasure to it is my pleasure to welcome him. Dr. Gahane, sir, you are most welcome.
Good morning, sir.
Good morning, sir. So I would like to present a brief biodata of Dr. Gahane, sir. Dr. Gahane, Professor Gahane, is working in NH College, Brahmapuri. He has a total teaching experience of 34 years. His major area of research is luminescence. He has done his master's and PhD from RTM University, Nagpur. To his credit, he has one patent, and he has 100 plus publications in national, international journals and conferences. He has attended one conference abroad in London. So this was the brief biodata of Dr. Professor Gahane. Professor Gahane, over to you, sir.
Thank you, Kage sir. Am I audible, sir?
Yes, sir. Yes, sir.
Okay. So good morning, friends. I welcome you all in second session of day 3 of International Online Conference on Advances in Physics, organized by the Gondwana University, Gadchiroli, in collaboration with International Academy of Physical Sciences, Prayagraj. At the outset, I am very much thankful to Dr. Ishwar Mohurle and his organizing team for assigning me the responsibility of chairman of this technical session. Friends, in this technical session, there are three eminent personalities are going to deliver their talks. namely Dr. Nilu Suryani, Udyana University, Bali, Indonesia, Professor Kishore Revatkar, Dr. Ambedkar College, Nagpur, and Professor Parmendra Kumar Bajpayee, Guru Ghanshiram University, Bilaspur. Before starting our first talk, I briefly introduce the first speaker. The first speaker in this session is Dr. Nilu Suryani. She is working as an associate professor in Department of Biology, Mathematics, and Natural Sciences faculty, Udyana University, Bali, Indonesia. She is graduated from Agricultural Doctoral Program, Agriculture Faculty, Udyana University, Bali, Indonesia. Their field of specialization is organic farming. She delivered keynote addresses and invited talks in various national and international conferences in different countries like Philippines, Thailand, India, Malaysia, and several countries in the globe. She received a grant of 90,000 US dollar from Udyana University and from high high education of Indonesia for concentration in organic farm research, such as development of local Balinese organic rice and other organic rice varieties. She received an award from a rector of Udyana University in the field of manufacturing innovative products in the field of organic agriculture. Actually, she manufactured 7 products: compost product, liquid organic fertilizer, biopesticides from Piper Caninium, biopesticides, local Balinese and organic rice, tea from local Balinese red organic rice, wine from local Balinese red organic rice. So, such 7 products manufactured by her. She won several research fundings competitions from the Director General of Indonesian Higher Education, LIPI Indonesia, and from Udyana University, Bali, Indonesia. She published more than 100 papers in reputed national and international journals. She such a eminent scientist with us. So I invite Dr. Neelu Suryani madam to begin her talk. Dr. Suryani madam. Kage sir.
Thank you for the time, Dr. Dananjaya. And thank you for organizer, Gundana University. And then thank you for Dr. Iswar Mohali as chairman in the conference. And then thank you for Dr. Faisal Fauzi in this conference, my friend, for the invitation for me as a speaker today. I'm so happy can meet in this conference, can sharing about my research about the Bali, very unique and special maybe today. I want sharing about it, about the sustainable concept in Bali. I would like to sharing about my PowerPoint. Excuse me, can see up my PowerPoint, Dr. Dananjay?
Yes, madam. Yes.
Okay.
Yeah.
Thank you. I will go to the topic today about the sustainable development system in Bali, Indonesia, in the International Conference on Advanced in Physics, organized by the Gondwana University. My name is Dr. Nilo Suryani from Bali, Biology Department, Mathematics and Natural Sciences Faculty, Udayana University. Bali is very famous maybe when you visit of my island, Bali, please visit my campus too because it's very near from the airport. Maybe 5 minutes or 10 minutes by car to from the airport. And then the main campus is included in the tourism area, like the famous big famous is Kuta Beach, Pecatu, Jimbaran Beach, and Huluwatu Beach is very near and very peaceful and quiet tourism area. Thank you. I go to the. I want to a little talk about the Bali now. Bali is a very famous number one destination of in the world, and then all people won't come to Bali, and yeah, we can see the attraction, the picture about the attraction of the tourism in Bali, like the Canggu Beach. Bali is very famous because it's very unique in the physics, like the sand, and it consists of the white sand, and then the uh, uh, culture is very unique, and the landscape is very unique. This is all is part of the Bali. Produce of the Bali in the sustainable development like this. You can see the picture about the Bali before COVID, but now is not like this, empty because close all the place of the tourism in Bali still close until now, and still work from home, and then the airport, international airport, is still closed. Maybe January next year is open. And then this is a question before the COVID. Very uh, useful of Bali because all of the people in the world they won't come to Bali because Bali is very attractive and in the many activity, culture, and the landscape. And then how to protect Bali still in the sustainable development. It's many uh, activity, many regulation from the Gubernur Bali and from the government Indonesia, special government Bali, make many regulation for protect of the Bali still in the sustainable development. This is my concept in Bali, how to protect Bali in sustainable development. Bali is a small island, and majority of the people in Bali, society in Bali, in the religion is Hindu religion, and all of the activity in Bali is collaboration with the culture, Hindu culture in Bali. Hindu religion, and the culture in Bali is two in one, and the mix is a good, excellent mix with Hindu culture and Hindu religion as a foundation of the Bali in the Indonesia. The first concept of the sustainable development in Bali is the name is Trihita Karana concept. Trihita Karana is maybe a Sanskrit language. Name is Trihita Karana. The mean is the tree is tree. Hita Karana is a habit of the Bali culture. Like this, consists of the three habits. The first concept is the good relationship for the God, and then the second concept is good relationship for the society, and then the third concept is a good relationship to the environment. and has three concepts in the Trihita Karana. This is the foundation of the Bali Hindu culture as the concept in sustainable development in Bali. This is Trihita Karana is one of the regulation from the government Bali. And then the other concept to the sustainable system development in Bali is the Subak concept. Subak concept is one of the society in the farmer in Bali to protect land, to protect the sustainable agriculture. The first activity in the Subak concept is the management water in good for the management water for the farmer, ex-farmer, and good for the relationship ex others in the farmer concept, and then the good relationship to the God too, like this. And this is the basic foundation of the sustainable development in Bali. And the other concept is the silent day. Bali is has the silent day. Silent day is one of the ceremony part of the Hindu religion. And then the one day the Hindu people, the Hindu society religion in Bali and the others religion, but stay in Bali cannot have activity, stop activity and stop to go to out, and then just stay in the house, in the home like this, or stay in the hotel, just stay in the hotel, and then and not go to the outside, and then the include in the airport to close in the silent land. Like this is very good to protect Bali to clear and green like this. And the other concept is the new concept. This is the Subak concept, Trihita Karana concept, and silent day is the traditional concept, a foundation of the Bali culture, Hindu culture. But now the Governor Bali has the regulation for the concept to the sustainable development in Bali is like the mix Bali clear and green. This is how to mix Bali clear and green. And include is the Trihita Kanal concept, Subak concept, silent day is include in the Bali clear and green. It's a good relationship uh, regulation with the traditional culture in Bali and the modern culture, modern regulation from the Governor Bali like this. And then the new concept in Bali is ecotourism concept, because Bali is number one. Maybe the society work in the tourism, and then how to make the Bali still in the sustainable development. But the other side, Bali is one of the place for the tourism, and the concept to mix tourism and the sustainable development in Bali to mix the ecotourism concept like this, and then the other concept is Bali for pilot project for the sustainable in the Indonesia for the sustainable development concept. Bali is for example like this pilot project. The first Trihita Karana concept is a good relationship to the God. Is the unique in Bali. We can see this is the Balinese house. The concept of the Balinese house like this. This is the modern, the traditional concept until now. The modern concept still a use of the Balinese house concept like this. Consists of the first, number one is Balinese house concept consists of the place of the photo frame. One place. This is area for the place. This is a good relationship to the God, like this. And the second building, the first building is for the frame, and the second building for the Balinese house concept for the room, for the sleep, like this. And then the third concept is consists of the Balinese house in physics is for the building for the ceremony, like for the activity for the married, activity for someone did, and others activity ceremony for the religion, like this prepare. And this place in the number 3, the third of the building concept in Balinese house, like this. We go to the number 4 Balinese house concept consists of the building for the prepare for the ceremony, prepare for the ceremony for the married and others for the deed of someone did, someone to prepare to the religion activity, like this. And then the number 5 is the concept welding concept in the Balinese house is for the kitchen. One building special unique for the kitchen. All activity for the making for the food, cooking in the building number 5. And then the building number 6 is building for the name is sieving for the food, like sieving for the rice, sieving for the others material for the food, like this. And then the under building in the number 6 is used for the like for the eat, for the meeting, like this, and for the party, Bali party, like this. And then number 7 is the concept for the toilet, like this. This is for the enter door from the outside to the inside. And then the 60% until 70%, the Balinese houses consist of the outdoor, and then the 50 until 40% are for the building, like this. This is the concept of the Trihita concept and the Balinese concept in the good relationship to the God. And this is the building, Bali House in Sustainable Development, like this. All material. This is the mix modern and the traditional style, Bali house style. This is the full of the traditional concept and the full of the technology of the modern concept, like this. You can see this is Balinese house is very unique. This is the door for the enter from the outside, and then the inner one of the building for the sleep, like this. You can see it's very unique. Consists of the stone, and then all of the material from the natural. We can see the other concept of the Balinese house building is the roof of the Balinese house is consists of the grass with grass plant, and then like this is very calm and comfortable, not hot and then not cool. It's a good for the concept of sustainable development in Bali. And then the other concept in the Balinese house is consists of the like this is plant, and then the just 30% for the building. This is example modern concept building in Bali in physics. You can see this is full of the technology and modern, but not change not most change from the traditional concept, but still in the traditional concept and mix technology from the modern concept. You can see this is the one of the other example from Bali, mix modern for a good quality house in the Bali like this. The second concept is Trihita Karana concept in Bali for the sustainable development is the good relationship to the society. One and its others society in Bali, people in Bali, Balinese people is a good relationship from maybe 1,000 years, maybe till now, still in the concept teamwork in the basic of the Hindu culture. Teamwork in Indonesia is gotong royong. In English is teamwork. All of the activity in the society in Bali, basic in the Hindu culture, foundation in the culture is all of the activity start from the teamwork work, like clean up, like the prepare the mid of the house, prepare the mix the river, recovery the river. This is prepare for the one of the ceremony in Hindu religion, like this ceremony for the marriage, for the someone did like this. All of in the teamwork. This is the foundation of the relationship to the society, include in the Trihita Karana concept. This is the activity in society, activity, all of the activity in the work, do in the teamwork, like this married activity, someone did like this. It's very, very unique when someone did in Bali like this. For the last of the meeting like this is the married, this is the activity of the ceremony in Bali religion like this is the temple, one of the temple in Bali, all of the activity in society in Bali for the sustainable development in Bali like this. We can see this is activity in the silent day here in the culture before I my experience in the Bali silent like this is all of the activity in Bali is stop for the one day, and it's good for the make the Bali green and clear for the environment, and include the airport, international airport close in the silent day. No watching, no internet. Just stay good for meditation, yoga, like this for 24 hours one day. The Trihita Karana concept is number 3. The third concept is a good relationship to the environment. Bali is very concerned, Governor Bali, society, and all of the people come to Bali, like the tourism, very concerned about the Bali still and clear and make Bali clear and clear, like the organic farm. My research about on the organic farm in Bali, and special for the local jenis species and red rice species in the organic farm. And then the many activity, all activity in Bali now is in the ecotourism concept, like the mangrove, photo tourism, and then but the others size is for the protect Bali from the abrasion from the still using for the fishing. And then this is many rice fall for the grand line in Bali. Cannot permit for the building, just for the rice fall like this. This is the one of the building in Bali in Pisik, Penglipuran village as ecotourism concept to sustainable development in Bali. We can see this is the very attractive, very interesting. All of the building in Penglipuran village is a concept in the Bali, traditional Bali. All of the activity, all the building are still in the Bali traditional. This is very attractive to tourism come to this village. Very famous, and then many education know about Bali. We can see all of the material of the house in the Balinese house like this. This is a concept of traditional. This is a very no, it's famous in Bali for the attractive for the tourism. The other side is Samsara Balinese house as a ecotourism concept. This is just example for many activity for the tourism ecotourism concept for the sustainable activity in Bali. This is as the activity for the mix of the one of the Balinese museum and the other activities and the food. All of the food here, a present a mix of the food used from the natural material and natural food. And then this is a good for the sustainable development in Bali. We can see the hotel concept in Bali. In Trihita Karana concept is the building consists of 40 until 50% in the building, and the outdoor is 70 until 60%. And then all of the hotel in Bali, the regulation from the government Bali is with the waste management. And then you can see the picture like this is very interesting and makes relax. Many people come to Bali to have to a relaxation, stay in Bali for the long time, and the many activity like the use land like this is very dangerous to for the Bali like this. And then the Bali protect for the how to protect Bali to change the use land. Like this is the one of the building in Bali, all material from the natural hotel. This is a building for government building like this. All of the material from the natural material. This is the school. All of the building in Bali, the regulation from the government is must use from the natural material. Like this, the maybe 50 or 60% using from the natural material like the stone, like the bamboo, like the wood. The other concept in Bali for the ecotourism concept in my research is about the sustainable agriculture concept. Include in the sustainable agriculture concept is consists of the organic farm like this. Many activity can develop in Bali, like the red rice is my research. This is the local species rice, and then the from the Balico, and then the Balinese orange, and then the snake crow. Like this is all of the species, the local species for development to the ecotourism concept for the international food. You can see the collaboration with the researcher, with the tourism, with the farmer, is collaboration to make the sustainable agriculture concept in Bali, like the organic farm, food tourism in Bali. Tourism come to Bali is very concerned about the sustainable agriculture in Bali and many benefits for the sustainable concept in Bali for the farmer, for the government, and for the tourism. It's a positive relationship. This is the one of the example of my research about the biopesticide from the fiberkininum extract from the plant, like this. This is the plant of the local species Bali can use for the biopesticide for the press of the blast disease on the rice in Bali, like this. Consists of the many phytochemical like the alkaloid, steroid, polyphenol, and flavonoid. This is the phytochemical can depress of the disease special for the blast disease on the rice. This is the one of the my product about the biopesticide. Name is caninum from the paper caninum extract. And then the biofertilizer, my product, like compost, like the liquid biofertilizer for the increase of the production of the red rice in Bali and the others rice. We mix biofertilizer and biopesticide to have the a good production red rice in Bali. This is the data about the biopesticide when we applied to the rice and consists of the many bioactive compounds. This is a potential for the biopesticide and good, and this is the application for the rice for the disease on the rice. This is the presentation of the inhibitory activity in the blast disease, and then the number of dialer, number of the leaf, the growth of the rice production, special for the red rice is increase the growth of the red rice. And then this is we comparison the treatment with the biopesticide and mixed with the biofertilizer in the organic farm. Part of the sustainable agriculture in Bali, when we comparison, this is the with the treatment with the biopesticide and biofertilizer. This is the without biopesticide and biofertilizer. Like this is a good production. Harvest is done in hectare to increase in the red rice when we comparison without the biopesticide and biofertilizer treatment.
Excuse me, madam.
Okay.
There is a time limit. Please take in short.
Okay, thank you. Just 1 minute maybe.
Okay, okay.
Okay, thank you. We continue. This is efficiency motto on the red rice in the sustainable development 2. This is the collaboration tourism, restaurant, all of material from the organic farm, take from the organic farm. And then the red rice to priority the product, my research, part of the Jatilwe organic red rice farm for the ecotourism concept. like this. This is my paper about the sustainability about the organic farm. And this is my team in the laboratory, my professor, Prof. Suprapto, and my friend Desi Anwar. Okay, this is my conference next time in the on the Augustus next year. Maybe I would like to invite you here to come to Bali. Maybe please contact me when you want to take this conference about the sustainable agriculture and ecotourism in Bali, include in sustainable development. The conclusion of the topic today presentation is one concept sustainable development in Bali is number one is concept Trihita Karana concept, and the second is Subak concept, and the third in ecotourism concept. And then the challenge of the sustainable development in Bali is land use change maybe, and then the negative effect in culture, and then change in style of the building. Uh, uh, Thank you for the attention for me in this presentation. The time is the Dr. Dananjaya, for the moderator. Thank you very much. Hello.
Now session is open for discussion. Are there some
Okay.
questions? Is there any question from participants? Kage sir.
Sir, there is one question in question and answer. The question is, do you have any biopesticides or herbicides for overcoming the fungus effects due to overwatering?
Okay. Thank you for the question. It's a good question in my topic. It is my problem in use of the biopesticide in the plate food on the rice. Because this extract, plant extract, phypercaninum extract is a good the material from the Bali is can solute in the water and apply mix with the water, no problem. And then the fungus like the blast, like the Pyrifluaria orsi, Nigrospora orisi, and the Curfularia orisi can depress from the my extract, pipercaninum extract, is mixed with the add with the water like this because it's a polar material like this. And then until now, we my research is for the easy in the shaping of the biopesticide. I mix with the in the my research with the EGPR bacteria, microbia like this for the fermentation, and then a good for the shaping of the biopesticide, and a good for the application in on the rice like this. Thank you.
Okay. Thank you, madam, for a very good presentation on sustainable development system in Bali, Indonesia. You
Thank
nicely
you.
presented the different concepts of sustainable developments, their parameter. I think everybody got the idea of your Bali bit and your research. Surely next time we will visit to Bali. As you said, next year you are
I
organizing
hope.
a conference.
I hope it's
Okay,
very nice, a beautiful island.
thank you, madam.
Thank you very much to all participants.
Thank you once
For the
again
nice,
on behalf of organizer,
okay.
Godwana University. Thank you, madam.
Thank you, Dr. Danantari.
Okay. Kage sir, Mungmode sir,
Yes, sir. Yes, sir.
shall I proceed? Second
Yes,
talk.
yes, sir. Yes, sir.
Dr. Revatkar sir. Okay.
Yeah, I am here, sir.
Revatkar sir, good
Yes,
afternoon.
sir. Good afternoon. Good afternoon, sir.
Friends, now we are in second talk of day 3, second session. The eminent personality, Dr. Kishore Govindrao Revatkar, is the speaker in this session. Dr. Kishore Govindrao Revatkar is professor and head Department of Physics at Dr. Ambedkar College, Nagpur. He is teaching UG and PG and postgraduate including nanoscience and nanotechnology. Recently, he is on board of studies in the physics in Gondwana University, Gadchiroli. Dr. Kishore Revatkar has authored 6 books for UG students of RTM Nagpur University and published chapters in internationally published books, and also in his credit more than 129 research papers in national and international journals. He received awards including Markins Who's and Who of America in 1999. His research is focused on development of nanoferrites, magnetic and electrical properties of nanoferrites, magnetic materials and ferrites for various technological applications. He is also reviewer of several international journals. 28 students have been received PhD degree under his able guidance, and 10 more students are pursuing their PhD degree registered at Nagpur University and Gondwana University, Gadchiroli. Dr. Kishore Revatkar has completed 4 major and minor research projects uh, from funding from various agencies like UGC, CSIR. 4 patents are on his name that are from Indian government. He has visited Sri Lanka, Thailand, Malaysia, Singapore, France, and so many, I think, entire globe he visited. Okay. So, such eminent personality is with us. I request Dr. Kishore Revatkar to begin their talk. Dr.
Okay.
Revatkar, sir.
Thank you, sir. Hopefully, I'm audible. Thank you for my
Yes, sir.
elaborate introduction to the audience. At the outset, I must congratulate the Gondwana University for taking this initiative and organizing a conference which will not only help the people who are working in the metropolitan city, but also some of the very good researcher and good faculties are working in official areas. So I once again I congratulate you, and at the outset I must thank you, Dr. Ishwar Morle, for giving me this opportunity to present my views and work with you people. In fact, I have worked with Dr. Ishwar Morle for almost 16 years in an institution wherein we have started our career as a teacher. So I'm very fortunate that the person like Dr. Ishwar Morle, I got, I can say, the colleague and work with him. So thank you. Good morning to all. Let me share my presentation. So hopefully my presentation is visible to you people.
Yes, sir.
Yeah, thank you. So minimize it. Okay. So today I'm talking on the scientific challenges and achievement of the 25th century and a perspective study. Now, as we are progressing toward the 21st century, lot of problems and challenges are in front of the humanity, and some are the natural challenges, you can say that, for our own existence, and some of the challenges that we have created, we human beings have created these challenges. So for that, we have to face the challenges and what are the measures that we can think about it. So my presentation theme is, I know I have 30 minutes, so I will finish it off in 30 minutes, well in time. So my scheme is, as I am basically working on a nanomaterial. So I'll be talking about a few of the nanomaterials and few of the recent advancement in the science and technology, and some of the challenges. So that challenges are environmental challenges and the challenge to the environment because of the pollution. And one of the major parameter that is very important that we have to think about it, we researcher, I can say that, not scientist I'm saying, because we are teachers also. So we as a researcher, we need to think about the global warming. So instead of going through the serial number 1, 2, 3, I would like to start with the challenges. What are the major challenges that we are facing? So there are a lot of major challenges, but out of which only 1 or 2 challenges I'll be discussing in 2 or 3 minutes, and then I will proceed forward to my talk. So one of the challenge that, as I told you, is a global challenge. So we are in 2020. So a lot of people have talked when we were at the verge of the 19th century. Then we were talking that by 2020 we can do this, we can do that, and the science will develop like this and like that only. So that lot of things that has been happening in and around. The science is developing to not to its pinnacle. So science is developing slowly with the pace, but there are challenges, and one such challenge is a global warming. So we are here, suppose we say that now it is everything is okay at the because we are in the month of the December at the end of 2020. But what time that this transformation will take place? So that we have to decide that by the end of which you can say that 20th century and 21st century, what we are going to do with the earth. Because this is what we have got and we have to preserve it, because we don't have another earth that we can ship from this earth to that earth. So we have to think about the one such criteria that for research we should take into the consideration is about the challenges that we are facing nowadays. Because we know because of the global warming, a lot of flood is there, and recent situation maybe 2-3 months back in Mumbai, that this flood, this picture is from Mumbai, as you can see. And we are day by day, we are adding to the, you can say that, to the worst of the situation we are adding with the help of the industrial, under the name of the industrial development. Then we can say that the jungle fire is one such area, landsliding is there, and the drought. So these are some of the effects of this global warming, you can say that. And slowly the climate that is also been changing. So we know that the increased temperature, we all know that the temperature of the earth that will be increased, and in the last 10 years we have noticed variation in the variation in the temperature, and that too you can say that on the higher side. So this contribution, so today this, you can say that the climate change is a global warming, and this effect has been created not only because of the one reason. So there are so many reasons, like you can say that the greenhouse gases are there, and this greenhouse effect is been there. One such greenhouse effect is because of the excess emission of this. So excess emission of CO2 that has created a problem, because whatever the radiations that will be coming from the sun radiation, so maximum radiations get reflected by the natural way, but some of the radiations that has been trapped down, and in particular I can say that about the infrared radiations that is been also emitted from the earth's surface, and they get trapped within the atmosphere, and that will be increasing to the temperature. And one such greenhouse gas is, you can say that, the CO2, methane, nitrous or oxide or chlorofluorocarbons, which was maximum times used in the refrigeration or the chilling work. One such effect of this will be there on the paddy field, because this Gadchiroli and this Chandrapur is a western either Vidarbha region wherein lot of paddy fields are there. So rice paddy fields have an adverse environmental impact because of the large quantity of the methane gas that is being generated from the during this season, paddy season. So this paddy season, so but we are not making use of this methane gas emission. We have not developed any kind of the technology that we can trap all this methane gas which is being generated during this paddy field, and so that we can use it for the other purpose. So methane gas can be used for the firework also, but that is been not there. And every year, if you find out the estimate, then there is about 30 to 90 million tons per year of the methane gas that has been generated or that has been developed during the paddy season. So we are not making use of it. So we are not thinking about that. And on the other side, we always try to show that we are not getting the good facility to develop the research work. We are not having a good research laboratory. We are not having a good funding. So instead of thinking and instead of crying that, I appeal all my faculty members and the students, budding scientists and the research pursuing students, that why can't they take a local problem and work on it? Something will come out of it. Out of the 30 to 90 million tons of this, you can say that the methane gas, even if we be able to trap 1 million ton or 1,000 tons of the, you can say that the methane gas, then that can be used. So that is also there. Then what causes the global warming? We all know that global warming is because of the so many things are there. So sun's heat radiation that causing a planet warm. The coal burning. So a lot of coal that, because Chandrapur Gadchiroli zone is a coal belt, then lot of coal that has been excavated from the earth and then it will be burnt up. So that will definitely going to create a lot of CO2. Because I know that this Chandrapur and this area, lot of dark color soot that will be falling down. The fog is there, and even the temperature in comparison with the Nagpur and other part of the Vidarbha region, the temperature of the Chandrapur will be always higher by 2 to 3 degrees. So that we have to think in a better way, so that we can develop a technology to curb with all these problems, and we can develop into you can say that the opportunity for that. So for that we have to think over that now. And we know that the earth global warming that will be there. So that global temperature, if you see, as I told you, that average temperature could be 3 to 9 degree higher than at the end of the century. So every year we can say that there is always a increase, and this particular part of the globe wherein our India is also been included into it. So we are also the sufferer, and we are also one of the victim of this global warming. So we have to think over this, so that this is one such area where the global warming, we can, even if we can contribute to a 1%, that we can reduce the global warming. So definitely we are going to help the humanity and the next generation that is been coming, because we have to hand over this earth to our next generation in a condition in which we have received from our ancestor. So but it is our main responsibility, it is our responsibility that we have to think over this, and we have to think positively. And there is a lot of development in the science, lot of development in the science, you can say that. So this is about the carbon footprint is there. USA is always using a lot of energy consuming and adding to a great extent to the carbon footprint, that means a global pollution. Though we are at the bottom, but sometime even if we can take this initiative, so definitely we can contribute to the to reduce the global warming. So that is important. So we have to, and these are some of the other things that can also be adding to the greenhouse effect and the you can say that the gas emission, but I'm not discussing those things. We all know. So This is a very important slide, which I think that at the 1990s, if you see, so we are at a very low with all these risks to the risk to unique and threatened system, frequency and severity of extreme climate events and global distribution and balance of impact, risk of irreversible large scale and abrupt transition. So we were at a low risk. But slowly, as this goes on, you can see these I have divided into 5 categories. So at the end of the century, by 21st, you can say that century, we can see that we were all been at a risk in all these areas. So we have to think and we have to possibly discuss this, you can say that this kind of the problem, and we have to make use of the all the resources judiciously so that it can be sustained, so we can have the sustained development. So these are some of the areas that has been already affected by the global warming and the climate change. That is what the consequences. So we have to think over this. Then there is another problem that we have to worry about it, and that is about the energy crisis. So whatever the natural fuel of that is been available there, like a petrol and the diesel and other fuels or gases are there. So we are taking out with a very high speed. So one day it will end. So we have to think the alternative ways by which we can have the sustainability on the earth, or the sustained development. So for that, we need to think about a technology, and one such technology is what I see, what I feel is a nanotechnology, because it is a upcoming thrust area where a lot of potential is there, lot of potential we can have in the nanotechnology, so that we can make use of this. So these are some of the major areas where the nanotechnology can contribute to the great extent. One such area is a renewable energy, but we have to think every time. We cannot look towards the developed country like the European or the other countries, that they can give the technology to us and we can use it. No, we should not beg every time to these people, because now we are educated enough. We should have to develop an attitude towards a small research kind of the small, you can say small sector, where we can develop our own technology. Sometimes jokingly we people are saying that a jugaad technology. Yes, that's true. So what is wrong in it? If that jugaad technology, that adjustable technology can give me whatever I want, in not only in one area but in all areas where we people require, like a textile, biomedical, healthcare, food, agriculture, industrial, electronic, environmental, and renewable energy source. One such management system, that is also one such area wherein we have to think over that. So nanotechnology is there. So let me start with this. So this all we know that we can work on a nanotechnology. Now people are working on a nanotechnology in the range of 10 to the power minus of 10 meter. But still there is a lot of scope that even we can go below that nanotechnology, even we can go up to a picometer. But still there is a, as the Richard Feynman has said, that there is a plenty of room at the bottom. So definitely there is a plenty of room, and there is a plenty of opportunity for we people to develop the materials, develop the system, develop you can say that develop the devices that can help us out for the better living. So I'm skipping some of the slides, but one such slide or one such area is that what is so special about the nanotechnology? What really? So we can tailor a bulk material into a small material or tiny material, so that the properties can be improvised. The same material you can take, and if we take the same material at the nano level, so we can develop the properties of that. Then the size effect is there, because all the nanotechnology only the size related effect and enhancement in the you can say that the sensitivity and etc. So at present even if we think about these 2-3 areas where we can make use of the nanotechnology, so definitely it will be going to. One such area is a medicine, energy, and certain material and electronics. So electronics, as we can say, in electronics, we have achieved you have taken a leap of step in which when we thought about the in 1980s, the 2 GB memory that has cost about the $80,000, then it has been reduced because of the advancement in technology, development of the technology. That has been reduced by in 1990s. The cost of this 2 GB was about something about 200, and now in 2020, even 2 GB we can say that about 1 terabyte we can get about the cost of 2,000 rupees, 4,000 rupees, not more than that. So for 2 GB, it is something about 350 rupees. So see how you can say that how a large leap that has been taken in the improvement of this. And today we are expecting the 1 terabyte memory that we can fit in at the tip of the pin, you can say. One such area is something like a transistor. As we are teaching to the students of graduate and postgraduate students that about the transistor. So now we have to teach then to the next generation, maybe after the implementation of the new education policy, is about the nano transistors. So now nano transistor are even one step ahead, we can go the tunneling electron transistor. So that has been also been developed there, so that with the help of the tunneling of the electron, the transistor or system that can be developed. So I'm not discussing much more about this, and I'm not going in the technicality of the problems. Otherwise, it will take a lot of time for me, and as the time constraint is there, so I'll be just giving the brief or the overview of the technology that has we have already developed. So Hewlett Packard HP company has developed a memory devices, and these memory devices, you can say that is a flexible devices that will be possible. So when we consider the register, then you can have the MEMS and the transistor, memistors, etc. Flash memory chips are been now developed, so that in a small area we can store large. Similar is the case of the display system. Similar is the case of the display system. मी काय म्हटलं खरडींचा एक 10-15 मिनिटं. So this display of the display system that we have developed. So because we have started with the CR tube, CR tube, even we can consider a CRO, cathode ray oscilloscope, or a television set wherein we can make use of a CR tube. Now we have changed from CR tube to OLED, organic LED, and quantum LED, even we can say that. So that is possible. That is because of, and even maybe we are expecting that in another 5 years we can have a very thin display devices that will be there, including your television sets and etc. So that can be foldable devices that will be possible. So with the help of the plastic sheet or polymer sheet, we can make use of that. So that is possible. We already know about the you can say that the mobile system. So mobile has also been changed from a lot. Earlier we had a small device wherein we have to press the button. Now there is a touch device, and lot of things that has been included in a mobile beyond the communication. So that is also been possible. One such area, as I'm telling you, that a nanotechnology in the energy. So we are using a PV cells, solar photovoltaic cell, you can say that. So these cells, where the majority of the material that is being fabricated or being used for the fabrication is a silicon or germanium or the semiconducting materials. But now with the advent of the technology, as there are certain limitations associated with the solar cell devices, because the efficiency is one criteria, one such area, that we have to raise a huge size panels of the solar cell. So that can be reduced by thinking of the another kind of the technology, that is multi-layer technology, because in a silicon or semiconductor technology, we are not using a multi-layer technology wherein the energy which is been falling is not been converted into 100%. The present efficiency is something about a 16% of conversion of the solar energy into the electrical energy or into the required form of the energy. So that can also be increased by using the multi-layer technology, and that multi-layer technology is a very simple technology, that instead of taking one single layer, so that whatever the radiation that can be trapped that can be falling on the cell can be absorbed, and maximum to I'm not saying 100% because it becomes the ideal case, but maximum 80 to 90% energy can be trapped down and which can be converted. One such area is the nano fabric. So that we are thinking about the fabric industry with the help of a nano material, wherein we can have the sensor connected to the fabric itself. We can have the display system. We can have the hydrophobic property, that is called as a water repellent property, so that we need not have to make use of the raincoats. Anti-static properties, so that it cannot develop a static current. Wrinkle free or wrinkle resistance, strength enhancement, so that it can have strength. It can also help us in blocking a UV temperature, and antibacterial or antimicrobial activity or odor control also. So that is been possible because of the nanotechnology. So we can develop such a nanomaterials, and by making use of the nanofibers, we can develop the fabrics. One such area is already been there. So nano sunscreens are there. Nowadays, the sunscreens are using, maximum times these cricketers are using, coating their face with the white kind of the powder. Now we cannot see the white color. So that is a transparent color. It is because of the nanotechnology. And the main component that has been used in the sunscreen lotion nowadays is zinc oxide and titanium oxide. And the advantage is of this material is that they can absorb the UV radiations, and they will prevent the screen burn from that. Then in the medical area, so a lot of changes are been there. So I'm not discussing much about the medical areas, but there is another material or nanoparticle that can be used for the phase change. Now, what is phase change material? So we can take a simple example of a water molecule, wherein we can know that at a temperature of about 0 degrees Celsius, the water from liquid to solid, the water can get converted at a 0 degree Celsius from ice, from the water to the ice, we can say that. Then at a higher temperature, it can convert from the ice to, that means ice to water. So that means a particular temperature which wherein we can say that a particular phase will be existing below that temperature, and above that temperature the other phase that will be existing. So this particular phenomena, if we use to the other materials, then we can say that the phase change material can have the high enthalpy. Enthalpy, this is a thermodynamic terminology. So this high enthalpy thing that will be used, so that which melts or solidifies at a certain temperature or phase change point, and simultaneously store and releases a large amount of the heat. So that means at a particular temperature, we can develop such a material so that they can sustain or they can retain that particular phase, liquid and solid. In case of a gases, it is not possible for us to have the phase change material, because the pressure, that is one such area will be there. So we can make use of the liquid and solid state, wherein we can have the phase change material. So these materials nowadays already been there in the market, but still lot of research is being required into it, so that we can develop such a good system. So nowadays everybody knows that the Asian paints are developed a kind of the paint where it can sustain the weather proof or water proof and heat proof and this and that, whatever advertisement they are giving. So what is been there? So they are nowadays using a nanomaterial, and to certain extent this phase change material, so that they can sustain it. Even a kind of the paint, I will come to that slide also. So this kind of the fabrics we can develop, so wherein we can trap the energy so that we can maintain the temperature of the room to be a lower temperature, or we can heat the temperature without using of the external heating source by coating this kind of the phase change material or paint, so that we can keep. Nowadays you can say that in a vehicle, car, a kind of different kind of the metallic paints that has been developed, so they are having the fluorescent kind of the you can say that the glow on the paint, and at the same time they are maintaining, because we know that if we keep our car close in the sun radiation, then after some time when we enter into the car, we find that there is a greenhouse effect, that because of the trap of the heat radiations inside the car. So such a paint when we develop, so they won't allow any heat radiations to penetrate, so that absorption or release of the heat that will be possible with the help of this paint. So thermostatic sleeping bags are there. In a extreme cold countries, this kind of the fabric that can be used, so with the help of which we can have the fabrics, so that can be keeping our bodies warm. So the heat dissipation clothes have been there. Some kind of the towels that has been developed, so that even if we can heat this material into the warm water and just shake it, the water will not stick to it, and again it will gives out the cooling effect. Or thermostat fabrics are also been there. Once this cold chain transportation, now we know that from one place to another place, if a material we have to transport, so any material, you can say that fresh vegetables from the farm to the various cities or to the various part, then in that case we have to carry them into a cold storage, you can say that the truck or chain. But in that case, lot of heat energy being required, the heating, because for cooling we require the lot of consumption of the petrol or consumption of the diesel, because we cannot make use of the you can say that the electricity directly on this. So, or we can generate it by placing a generator, then again we require the diesel and the petrol. So by coating this material, we can keep the refrigeration work or the incubator container cool to a larger time, so that we have to develop, customize. So then room cooling system for this cell, or heat dissipation batteries can also be developed in such a way that there is a loss associated with the energy that will be less. Then nowadays the mobile phones, because if we use excess use of the mobile phone, if been there, then we find that after 10-20 minutes the mobile screen gets heated up. So by using of this kind of the phase change material, we can keep the temperature of the mobile, because even after the excessive heating, we find that the mobile gets heated up. And likewise is the case of the motor cooling also there. So that has been possible. Then thermostat can also be in there, water heaters, and there are so many applications of these are there. In market, it has been already there, but still we require to improve it, because they are costly affairs. Costly things are there, so we can reduce it with the help of the local technology. This I was talked about paint. So this kind of the coating or the paint, which are micro encapsulated phase change material used in the building interior or exterior wall coating, which can reduce the frequency of indoor air temperature fluctuation, or keep the temperature close to the required temperature we can maintain. We can regulate the temperature, so that increase in the human comfort that is been possible. So these are the phase change material, and they are not it is not you can say that we don't require a great technology to develop this kind of the things. We require a small technology, so with the help of which we can do it even in the laboratory condition. Yes, I am talking undergraduate level laboratory also, we can develop this kind of the paint. Dhananjay sir, can I have 5 more minutes? Yeah, so this is what I was talking, the room comfort. Then keep the ground temperature and greenhouse energy savings are there. Another area wherein, hello, am I audible?
You are audible, sir.
Sir, can I take 5 more minutes? because I know I have crossed my limit of time.
Yeah, sure, sure. You can take,
Oh,
sir.
thank you, thank you. So nanocomposites is one such area wherein we can sandwich so many different kind of the phases together, and we can develop a material like nanocomposites. We can say that a metal nanocomposite, different kind of the metals we can take, wherein the core shell and the alloys we can take. Metal and ceramic nanocomposites is one such area where a lot of development that has been done to a great extent in ceramic nanotechnology. So zirconia, tungsten, alumina, and etc. These are some of the polymer based nanocomposites are there. So, and likewise nylon 6, N6, this MMT with silicates, bio nanocomposites is one such area wherein we can develop these things are there. So why polymer nanocomposites are unique? Because we can increase the electrical breakdown strength of the polymer. So that is one such area. Melting temperature that can be control or maintain, the color, magnetization, and change in the capacity. And likewise, there are so many areas where they are there. And the areas wherein this find their applications are catalyst in the battery for the energy saving. Nowadays we are talking that when we procure a battery, even a car battery, so the life of the car battery is something about 2 years. So that life we can increase, and then we can reduce the total weight of the battery, strength of the battery, and lifespan of the battery with the help of the composites. Then artificial joints, that is been possible. Then abrasion and wear applications are there, and marine food packaging, fuel tank, film, this and that. There are so many applications are there. Such application is directly, we can say that, in the development of the aeroplane. So in case of the aeroplane, nowadays the advanced composite materials that has been 50% that has been used. So outer body of the aeroplane, inner body of the aeroplane, so that the weight that has been reduced to a greater extent. And because of that, you can say that because of that, the fuel efficiency that has been increased. Nowadays only 10% of the steel, that is the primary landing gears, that been used for the aeroplane, while the 15% of titanium, 20% of aluminum, and 50% of the advanced composite, which is lighter in weight, that can be used, so we can reduce the efficiency. Then there are other advanced materials are there, and these advanced materials that we can talk about a ceramic. Then the sensor material, you can say these are very important sensor material. So with the help of the sensor system, we can do the sensing without any physical contact. So wireless sensors are there, gas sensors are there, liquid sensor, different kind of the sensors are there. Then optical fiber and conductive polymers that can also be there. So you can say that, so in a popular ceramic, these are some of the ceramics that is they are known as a conventional ceramics. These conventional ceramics are being used, which are have the high strength and have the retention at a higher temperature, means higher temperature retentivities are there. So some of the areas of the ferroelectric sensors, you can say that. So I'm skipping some of the slides. So some of the smart systems we can develop. So with the help of this kind of the materials, composites, ceramics, polymer, then alloys and crystals are there. And then these smart systems require basically your sensor, your electronics associated with that for the processing of the information, and the actuator, which are being used for moving, positioning, and regulating of the control system. So that nowadays people are thinking about a smart home control system, that if you have a smart control system wherein you can control from a distance place, even if you are at an office, you can control your you can switch off or switch on your television, then you can switch on or switch off your what's a washing machine, then light system, and Wi-Fi, this and that. And the main requirement, even you can have the house protected from the burglary. So for that, you only require the Wi-Fi system. And nowadays, because of this pandemic, this internet was the basic need. The one such thing that has been added in the layman's life is about the Wi-Fi system, and everybody is procuring that. So definitely this will be going to help the smart control system. And lastly, but not, because this is my area where I work a lot. Many times we think that whatever your areas are there. So I am talking about that. So the possible application of magnetic materials that we are doing is the protein separation that is being required, magnetic guidance of the cell, removal of hazardous material from the waste water, degradation of pollutants and etc. Then this is one such upcoming pop-up area wherein microwave dielectric been there, the patch antenna. So this patch antenna, nowadays we are using a mobile phone wherein we are using a patch antenna, and the frequency range which is being used for the patch antenna is 35 megahertz to 2.5 gigahertz. This is I am talking about, you can say that the 4G technology. In the 4G, at present technology been using this range. 5G, it will be more than that, up to 5 gigahertz. Then 3G technology was up to 1.5. So this 2.5 gigahertz is the frequency of the microwave oven. To be very specific, I am telling you, 2.45 gigahertz is the frequency at which the microwave ovens are working. So we are using that frequency. So of course they have certain side effects on the bodies, but still we are using. So we can make use of these technologies with the help of certain dielectric, microwave dielectrics, so that the technology that can be developed. And one such area, as I told you, the microwave antenna and millimeter band waves, wherein the dielectrics can be used for the lightweight, low cost, small size, high radiation efficiency, and large band width also. So these are some of the designs of the patch antennas that we have developed in my laboratory, and we have used and we have patented this one such 5G antenna which we can insert inside the body for the hyperthermia application. So that is under process. So, but we have got the patent on this 5G antenna. Now then another area, as I told you, the solar cells. Present technology of solar cell is been using a silicon, only single layer, but with the help of a multi-layer silicon, we can make use of the multi-layer silicon, wherein we can increase the efficiency from present efficiency of 17% to 27% efficiency that has been achieved. And these are some of the materials that we have developed in the laboratory. Yes, in my laboratory, as Dhananjay sir knows, my college is also UG and PG college. So we have developed this material, and these are some of the solar cells where we are making use of it. So we have done this. And finally, when we develop the technology, we know that in 2009, when a person has to take the video shooting, maybe you have seen a picture, Chandani, one who did that Rishi Kapoor has taken the video shooting of that Sri Devi, because both have gone in the heaven. So that time they require the manpower, but in definitely 2019 or 20, just 10 years, cameraman that has been gone down, and we know that this kind of the drone that has been developed, so which will be definitely, we have upgraded our technology, but at the same time we are losing the job. So we have to develop this thing. So when we consider, we started with the technology like this, the punching of the nail in the wall, where then we have come to the grill, and then another system, and slowly we are reaching. So one day it will come that this robotics will kick us out and all technology will be there. So we have to think about it. So thank you very much. I'm sorry I have taken a little bit more time. Thank you. Any question? Yeah. Sir, I have over.
Gane sir. Gane sir. Hello.
Is there any question? Kage sir, am I audible?
Yes, sir. Yes, sir.
Yes, sir, you are audible, but I think there is no question.
Yeah, I think they are tired.
Okay, thank you,
From last,
sir. But you
from
have
last
deliberated very well informative talk on scientific challenges and achievements
advancement.
of
Yeah,
the
thank you, sir.
21st century.
Thank you, sir.
Actually, I am very happy with your appeal. That is, do the research in research on local problems which are useful to the local society. I think our young researchers, beginners will accept this challenge. Okay, thank you, sir. On
Thank you.
behalf of Gondwana University, once
Thank you.
again, and thank you to you. Thank you for delivering very nice talk. Okay, thank you, sir. Friends, our third talk was from Bajpayee, sir, Professor Parmendra Kumar Bajpayee, sir. But due to some technical problem, he is not available. Therefore, this talk is cancelled, and I think I hand over the control to Dr. Kage, sir. Kage, sir, please.
Thank you very much, sir, for chairing this session wonderfully. Now, I request the Dr. Vishal Panse to please continue for the technical session, of oral presentations. So, for this session, we have Dr. Vishal Panse as the chairman. Panse, sir, please. Dr. Panse. Dr. Panse.
I think he will be there within few minutes.
Okay, sir. Fine.
Kage sir, hello, Kage sir.
Yes, sir. Yes, sir.
Uh, till now, what we'll do, we'll take all the attendees who are going to present today on the panelist. Right.
Okay, okay, okay.
I think the list is available with you. So
Yeah, yeah.
let
I
us,
will.
technical team. Yeah.
Yeah, yeah. I will coordinate with the technical team in this regard, sir.
Vishal sir. प्रॉब्लेम सॉल्व्ह झाला का? हॅलो.
येस सर.
नाही, पानसे सरांना म्हणतोय प्रॉब्लेम सॉल्व्ह झाला का? त्यांना ऍक्च्युली दे आर कनेक्टेड बट आय थिंक दे आर नॉट ऑडिबल. ऑडिबल मीन्स देअर व्हॉइस इज नॉट ऑडिबल.
He has muted, I think. He need to unmute himself.
Okay, I will tell him. I'll tell him. Pancha sir. Hello. Okay, sir. Hello. Okay, sir. Am I audible?
Yes sir. Yes sir. You are audible, sir.
I think he has some technical problem. So till now, I think we should continue.
Okay. Okay. Okay, sir. Fine.
Right. So Kage sir, I think we should continue now because he has some technical difficulty. Sir.
Pancha sir. Pancha sir.
Kage sir, now we'll continue. Saman Operanti is, I think, there. He can make his presentation.
So whom to make presenter?
Saman Operanti, he is in attendee list.
Okay. Uh, yeah, we shall make him panelist now.
Yeah. Till now, Angelina Dorothy is, I think, there.
Yes,
Right.
yes, yes,
So, ma'am, am I audible to you?
yes, yes. Am I audible,
Okay.
please?
Yeah, ma'am. So,
Okay.
you can make your presentation. Kage sir, make Angelina Dorothy ma'am presenter.
Yeah, sir. Yeah.
Okay. So what do I do, sir, now?
1 minute, ma'am. They are making you a presenter. Then you can share your PPT.
Okay.
Okay. Now you can present your presentation. Ma'am.
Okay, sir. Thank you.
Yeah. You are audible now, so you can continue now.
Okay. Shall I start?
Yeah. You, ma'am. You
Okay.
can start.
Okay. Good afternoon to all of you. My name is Angelin, and I'm working on the field of band gap engineering of TiO2 as a visible light photocatalyst. So we are using the first principles DFT theory. And let us first consider what exactly is photocatalysis. It is nothing but the catalysis under light irradiation. And in this, the photons are used to activate a semiconductor, and thereby electrons and holes are generated. And we can excite, and the semiconductor absorbs the photo energy to promote an electron from the valence band to the conduction band, thereby bringing about redox reactions, chemical reactions. So when you look at photons, we can see that sun is an almost infinite and costless source of energy. We can use this clean and sustainable energy source for properly solving all the energy problems which is caused by the depletion of fossil fuels. So it is a reliable and diffuse and intermittent source of energy. And the semiconductors that we use can cause chemical reactions upon light absorption, particularly the sunlight. The why semiconductors? Because they have this high, and when we can even use nanostructures, they bring about high surface to volume ratio that increases their capability to harvest solar radiation. So we can use this free source of energy to bring about chemical reactions and generate energy. Their tunable properties are another advantage that allow manipulation of their energy levels. So photocatalytic processes that turn solar energy into chemical energy. So now one of the semiconductors is TiO2, and we see that it is an N-type semiconductor, and the applications it has wide and extensive applications ranging from heterogeneous catalysis to dye-sensitized solar cells. It has tunable properties of their energy levels. So this is the structure of TiO2. It exists in three polymorphs: anatase, rutile, brochite. So in order to, and we see that the band gap is 3.2 electron volts for anatase. The structure is 001 facets and 101 facets. So when it is absorbing in the visible light photocatalysis, to make it to absorb in the visible light photocatalysis, we have to reduce the band gap. 3.2 corresponds to the UV region. So we have to sensitize it to bring it to the visible light. So the TiO2, it operates effectively under, to make it operate effectively under ideal solar sunlight, that is sunlight, we have to, which is 54% of it is visible region, and only 4% is in the UV region. So we have to develop a smart catalyst which can absorb UV and visible light. So we can bring about this by quantum confinement, anion, cation doping, and crystal facet engineering. So what is the role of noble metals? We can dope our TiO2 with noble metals because the noble metal dopant decreases the non-radiative recombination of the electron hole pairs, so which are necessary for the chemical reactions. We can increase the lifetime of the photoexcited electrons and holes for effective reactions. What are the methods we are using? Density functional theory and a computing cluster. And the code that is used is developed by the University of Vienna, which is called as VAST, Vienna Ab initio Simulation Package. This is the cluster we have used, the master node and nodes. Then WASP is nothing but a computer code for materials modeling, where we have used 1 electron orbitals to perform the electronic structure calculations and quantum mechanical molecular dynamics. We are able to calculate the ground state properties, total energies, band structure, density of states, phonon spectra, etc. So the approach is supercell approach. We have used DFT calculations, and we dope 1 titanium atom each with a corresponding dopant metal atom. But the cutoff plane energy, plane wave basis set is optimized to be, we found it to be 550 electron volts. Our accuracy is convergence was at 1 into 10 power minus 7 eV, and maximum force acting on the atoms at 10 power minus 3 eV per angstrom. So this is the pristine supercell TiO2. This is the density of states, or the band gap that we are getting. This is for the pure TiO2. Now we are doping it with platinum, 1, 2 platinum atoms, 3 platinum atoms. So for the 1 platinum atom, we see that the band gap is reducing a little bit. And this is the charge cloud, that is the charge density plot. You can see that the platinum and the oxygen, there is a charge cloud forming between them. This is for the 2 atoms. Now here again, we see the band gap getting reduced. This is a charge cloud between platinum and oxygen. For the 3 platinum atoms, we see that the band gap is much reduced and the charge cloud is this. So, and the same case which happens to the silver atom. When we dope it with 1, 2, and 3 silver atoms. Here we see that there is a difference in the density of states. We see that there is a shift of the bands towards the right of the Fermi level. This is the Fermi level for the spin down electrons. So the oxygen neighboring to the atom also, they lose charge, which mostly gets transferred to the spin down channels of the nearby oxygen atoms. Here it is a little different. Of course, the band gap is reducing. We see for the 3 atoms, it is reduced much. So this is our formation energy band gap. You see the platinum and the silver, the band gap is reducing as we increase the content of the platinum or the silver atom. We can also perform the optical properties by these calculations, where we can find the dielectric constant, and then we can find from the imaginary state and the real state, we can find out the optical properties. So let us look at the optical properties of these doped substances. The absorption edge now, you see when we dope it with silver and with platinum, this is for the pure, the black is for the pure. When we dope it with the dopants, the absorption edge is coming to the visible light, to the lower energy. Then we can see the electron energy loss also. The ELF peak goes on decreasing, and at lower energy levels, the UV is to visible range of the energy spectrum. Okay, so then when we can see for the extinction index also, the silver and platinum doped TiO2 have high extinction peaks in the UV to visible range. Then reflectivity, we see that the reflectivity at lower energy range is more compared to the pristine TiO2 for the doped substances. Then when Ag is doped, there is much higher index, the refractive index is very high, very much high for the silver dope compared to the pristine, which is at 2.76, that is a pure TiO2. The refractive index attains its minimum energy from 0 to 0.1, where absorbance is maximum. This is the dielectric function. The value of the static dielectric function for pristine TiO2 is 7.6, and that of platinum doped is 8.6, and for silver it is 920, making the silver dope almost metallic. So now we have also worked on the 101 and the 001 plane nanosheets. This is a 001 surface. We have made a nanosheet out of it just by calculations, and we also by 101 we have made facets. We have made a nanosheet. So this is the nanosheet. This is for the 001 and this is for the 101. So we have studied the partial density of states of the bulk. This is how the bulk partial density, that is of the various atoms. This is for the 101 sheet of the nanosheet made out of just 101 facets. And this is for the 001. So here we see that the Fermi energy is crossing, the conduction band is crossing over the Fermi energy, making it almost metallic, little bit metallic. When you look at the properties, optical properties, this is the dielectric coefficient, the imaginary parts, we see that the for the bulk it is almost same. We have considered the three directions. In the three directions, we see for the bulk it is almost constant, whereas for the 001, the two xx and yy it is same, whereas for the 0zz it is different. Whereas for in the 001, we see that the dielectric constant is different for each and every direction, making it anisotropic. That means 101 is more anisotropic than 001 compared to the bulk. Same way we see for the real part also, we see that the anisotropy is more in 101 compared to 001 compared to bulk. You see the anisotropy is very different. When we look at the absorption coefficient, we see that the absorption coefficient for 101 is very less, whereas for bulk it is quite high. And compared to the, for 001 it is less compared to 101. So electron energy loss spectrum also, you see that the electron energy, we see two peaks in the bulk, whereas this peak is shifted towards the left for the 001 and the 101 nanosheets. So the extinction coefficient also, we see that the extinction coefficient is again, it is anisotropic, it is much less for 101, and for 001, it is showing a lesser value than the bulk. For reflectivity also, we see here in the reflectivity, it is showing in the lower regions. For 101 and 001 and bulk, we see that the reflectivity is better in the lower regions, energy regions. And the refractive index, 101 is having a high refractive index compared to the bulk. And you see even the 001 is also having anisotropic refractive index. So now let us look at the chromium. In the chromium, we have studied that the PDOS, that the density of states is having, this is the oxygen 2p, and in the literature shows that the chromium is having, the Fermi energy is crossing over the conduction band. And this is what we have also found. We have seen that the Fermi energy is crossing over the conduction band. And this is the density of states we have seen in the chromium. Then next is for the silver, we have for the gold, we have seen that gold does bring about visible light photocatalysis or visible light radio interaction photocatalysis of PiO2, and we have seen this is the PDOS of the gold doped PiO2, and this we see that this is the red is the titanium 3d orbitals, and oxygen is the green, and the oxygen is the green, and the gold that is interacting well with the titanium 3D and the oxygen 2p. In the valence band, we see more of the oxygen, and in the conduction band, we see more of the gold and the titanium dominating. Not 2p is not, oxygen 2p is not dominating. So as conclusion, the band gap of TiO2 has been lowered as concentration of Ag under platinum dopants increases. The electronic structure shows strong hybridization between titanium 3D and Pt platinum dopant 3D levels in the valence band. The charge difference plots show a platinum oxygen and silver oxygen charge cloud being formed, indicating a cationic platinum or silver and charge accumulation on oxygen. So optical properties indicate visible light activity for the doped TiO2. Now let us look at the nanosheet result. The TiO2 101 plane shows a band gap of approximately 1 electron volt, and the 001 sheet shows a semi-metallic state because the Fermi energy was crossing over the conduction band, whereas the bulk shows a band gap of 1.5. So we see a reduction in the band gap. Complex dielectric functions and optical properties of TiO2 001 and TiO2 101 with that of the bulk, we see that the optical anisotropy in the 101 is very high and is evident in both the sheets. TiO2 101 has greater anisotropy, making it a useful optical material. 001 nanosheet shows anisotropy in two directions, XXVI equal to YY, not equal to ZZ, whereas in 101, their anisotropy is different in all the directions, XX, YY, ZZ, and XZ. The optical properties and dielectric constants definitely point to possible enhancement of the visible light activity. We saw that all the doped were showing visible light activity in the cases of the 001 and the 101 nanosheet compared to their bulk counterpart. So the summary is the doping of silver and platinum has produced favorable lowering of the band gap to visible light in TiO2. Structural, electronic, and optical properties indicate such doping is favorable. The reflectivity and extinction coefficients in the nanosheet, the 001 nanosheet, could be help that it could be used as a better reflective material. Whereas the extinction coefficient and absorption coefficient for PiO2 101 was high. They indicate that they have better absorption properties. So these are the references and these are the publications we have made so far. Thank you so much for your attention.
Thank you, ma'am.
Okay, sir.
Dr. Vishal, here I think he has lost connectivity. So anyway, we will continue. So once again, I'm very thankful to Dr. Anjali Dorothy, ma'am.
Thank you so much for the opportunity.
Okay. Next presenter is Dr. Shashikant Gedam. Kage, sir. Okay. Gedam, sir, am I audible? You can make your presentation now. Gedam, sir. अनम्यूट करा तुम्ही अनम्यूट करा स्वतःला ते अनम्यूटचं एक हे असेल
सर अनम्यूट केलेला आहे गेडाम सरांचा
हा नाही नाही गेडाम सरांना म्हणतोय मी
हो गेडाम सरांचा अनम्यूट केलेला आहे सर
आवाज येत नाही त्यांचं आय थिंक गेडाम सर तुम्ही अनम्यूट करा स्वतःला खाली टॅब्स असतील स्टार्ट व्हिडिओच्या जवळची एक टॅब असेल बघा
Sir, he has muted himself.
Yeah,
now he's on mute. He is on unmute mode.
Gedam sir, you can speak now.
Gedam sir, you are not audible.
Sunil?
Yes, sir.
सुनील तिकडे गेडाम सरांसोबत आहे का
नो सर नो सर नो 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 मी बाहेर आहे दुसरीकडे
ओके 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 गेडाम सर यू कॅन अनम्यूट युअर सेल्फ
सर गेडाम सर ऑलरेडी अनम्यूटेड
हेडफोन लावून करा मला सांगायला पाहिजे
हेडफोनच मला वाटतं लावलेला आहे सरांनी सर हेडफोन काढा बरं हेडफोन काढा आणि असंच करा काढून घ्या तो मायक्रोफोन हा डिटॅच
हॅलो
नाउ यू कॅन स्पीक हा या यू आर ऑडिबल नाउ हा चालू करा सर यू आर ऑडिबल
टुडे टू respected all organizers today I am going to represent the paper on the topic of dielectric measurement of benzonitrile and acetylnitrile in benzene solution at microwave frequency. In this paper, I am the main Shashikant B. Gedam, along with myself, Sanjay B. Nagdevte and Sunil Chute from the Department of Physics, Amalokchan Mahavidyalaya, Yotmad. Loss factor of benzonate in dilute medium at room temperature and at the frequency of 10.15 determined experimentally using Smith's equation. That is the Gopal single frequency method based on the Debye equation has utilized to analyze dielectric constant, that is epsilon dash and epsilon 2 dash, to obtain the relaxation time and dipole moment mu are utilized to explore the molecular structure. The value of relaxation time and dielectric electric dipole moment mu are obtained in this way. In this investigation are encouraging by in agreement with the literature value. The keywords are the dielectric constant, dilute solution, microwave frequency, and dipole moment and relaxation time. The basic introduction for this study of dielectric constant of a polar liquid, especially in the dilute solution in a non-polar medium, have very important role structure to liquid. Dielectric constant is molecular property of substance. It is due to the contribution from orientational vibrational polarization. Dielectric mainly probe weak forces to understand the intermolecular reorientational dynamic constant. In this paper, we have carried out dielectric measurement of a polar liquid benzonitrile and acetonitrile in a non-polar medium, that is the benzene, at a micro and single microwave frequency, that is 10.15 gigahertz, and it is at the room temperature. The result of this, the results are discussed to interpret molecular structure in terms of relaxation time and electric dipole moment of reorientational motion of the dipole in the medium. The method is used for to determine all these things. That is the benzonitrile and acetonitrile. In the non-polar benzene is required for that. So we have purchased the AR grade material and use it is without purification. The dilute solutions of the acetonitrile and benzonitrile, we make the dilute concentration in the benzene, and we in a well stopper volumetric flux to ensure good thermal equilibrium. These systems are assumed with dilute solutions. The X-band microwave bench was used to measure the wavelength of the microwave radiation in the liquid dielectric cell. The liquid sample was held vertically in the liquid cell by supporting a thin mica sheet whose VSWR and attenuation are assumed negligible small. The liquid dielectric cell was attached at the end of the microwave bench and maintained at the room temperature. So the X band microwave bench and this system is as shown in this photograph. So this is my experimental work by which we have carried out all these things. These are the equations, basic equations, and from this we are finding on this all these values of dipole constant and relaxation time. So result and discussion. So for the different compound, that is the benzene, benzonitrile, and acetonitrile. So these are the molecular weight, melting point, boiling point, refractive index, in the density of the benzene, benzonitrile, and acetonitrile. To determine the values of dielectric constant and dielectric losses of benzonitrile in benzene medium, it is reported in this table. So this is the weight fraction, benzonitrile. So from experimentally we are getting this is these values are the dielectric constants. This is the losses, and these are the parameters by the formula we have calculated that the value of x and y. That is just the concentration is going to changes. That is the weight fraction is changes. So we are getting the variation for this. So we have, to determine the relaxation time and dipole moment, we are going to plot the graph between y and x. So we are getting the linear behavior between the y and x there. After that, to determine x and w, to determine the relaxation time and dipole moment, we have to plot this graph between the x and w. And again, this is the it has the linear behavior. After that, for the second component, what is the acetonitrile? We take the different concentration of the acetonitrile in this benzene medium, and we have calculated experimentally the value of dielectric constant in the electric losses. And from by the formula we have calculated the parameters x and y like this. After that, again for the same as to the previous, to determine the relaxation time in dipole moment, again we have to plot it between the parameter x and graph, the linear behavior in between the x and what we are getting here. Determine the relaxation time and dipole moment, we plot the graph between the x and w. Again, it have the linear behavior. So conclusion of this, the values of dielectric constant, that is the epsilon and dielectric constant of benzenitrile and acetonitrile at the dilute solution of benzene is increases as the function of concentration of polar substance, and it is vary with the concentration of solution where sufficiently dilute to minimize dilute interaction. The values of relaxation time, that is tau, that is equal to 7.7656 ps, in electric dipole moment, that is mu 3.8499 d of the benzonitrile, and for the acetonitrile relaxation time is 7.4550 ps, and electric dipole moment, that is mu, that is 3.526 d, that is for the acetonitrile in benzene medium, and that is agree with the values quoted in the literature. So so these are the my conclusion, and my acknowledges with our principal and the management who encourage me for this for the research purpose, and I am also thankful to the UGC for giving me the opportunity of FIP. These are the my references. I am going to do all this research work. Thanks, sir. Thank you very much, sir.
Thank you very much, Gedam sir, for presenting, for sharing your research work with our participants. Now we are heading towards our next participant. That is according to our list. The first day we had Dr. J.M. Bhandari. Okay, due to some technical reasons, he could not presented his work. Now today he is ready. So, Kage sir. Kage sir, am I audible? Dr. Bhandari is there. Dr. Jawaharlal Bhandari. In attendees, take him to panelist and make him presenter.
Hello.
Hello.
Sir. Hello. Am I audible, sir?
Yes, sir. Okay, you are audible, sir. You are audible, and you can now make your presentation.
Sir.
Sir, all the participants should note that the maximum limit time is 5 to 6 minutes. So within that time, you should have to conclude your presentation.
Sir, my presentation is visible.
Yes, sir. Your presentation is visible. You can start now.
Good afternoon to all of you. First of all, thank the organizing committee of this conference for providing me such an opportunity to present my research work before all of you. Myself, Dr. Jawaharlal Bhandari from SK Gandhi Arts, Science and Commerce College, Kada. Today, I shall present my research work entitled Study of and Electrical Properties of Nickel Copper Spinel Ferrite. Outline of this mainly consists of introduction to ferrite, result and discussion, and conclusions. Introduction. Ferrites, being a magnetic material, have been the subject of interest for the academician and technologist since 1945. Ferrites are complex magnetic oxide that contains ferric oxide Fe2O3 as their main component and metal oxide. The technical importance of ferrite lies in their high electrical resistivity, high saturation magnetization, high permeability, low eddy current and dielectric loss, chemical stable and low cost. Ferrites are the materials of great importance in technological applications on account of their combined electrical and magnetical properties. Ferrites have vast range of application from microwave to radio frequencies. Now here in this figure shows the various applications of ferrite. Now the aim of my present work is to study of structural and electric properties of copper substituted nickel ferrite. Experimental techniques. A polycrystalline spinel cubic ferrite powder with Ni1-X CuX Fe2O4, where X is ranging from 0 to 1, 0.0, 0.4 and 0.8, were synthesized in a stoichiometric ratio by standard technique using NiO, CuO and FeO3. Structural studies were carried out X-ray diffraction for 2 theta values ranging from 20 to 80 degree using CuK alpha radiation at lambda is equal to 1.54 angstrom. Lattice constant and X-ray density were calculated using the XRD data. Now, electric and dielectric studies. The DC electrical resistivity of different temperature from room temperature were measured by using the two-probe method using the relation rho DC is equal to pi r square upon T r ohm centimeter. Dielectric measurement as a function of frequency at room temperature were measured by LCRQ meter in range 100 Hz to 1 megahertz. Dielectric constant, dielectric loss and dielectric loss tangent were calculated by using these formulas. Now the result and discussion. A X-ray diffraction analysis. The X-ray diffraction pattern, that is XRD, of all the synthesized NiCu ferrite are shown in these three figures. The XRD patterns clearly indicates the formation of single phase spinel structure. The X-ray diffraction pattern shows intense, clear and sharp peak which are indexed using Bragg's law. The Miller indices 220, 311, 222, 400, 422, 511, 440 and 533 belong to spinel ferrite is observed in the XRD pattern, in which 311 is the high intensity plane. By using the XRD data, lattice constant and X-ray density were calculated and are shown in these figures. From figure, lattice constant increases with increasing copper content X, while X-ray density decreases with increasing copper content X. Because Ni2 plus ions with ionic radii 0.69 angstrom takes place by Cu2 plus ions with ionic radii 0.72 angstrom, the values of bulk density, porosity and particle size are also shown in the table. Now the analysis of electrical properties. First, the DC resistivity. The plot of logarithm of resistivity versus reciprocal of temperature is shown in figure. It is observed from this figure that the resistivity of the present samples decreases with temperature obeying Arrhenius relation. The variation of DC resistivity is linear up to Curie temperature Tc, at which ferrimagnetic material changes over to paramagnetic state due to the influence of magnetic ordering. Now the analysis of dielectric properties. First, that is the dielectric constant. The variation of dielectric constant measured as a function of frequency for all the samples under investigation of at the room temperature are shown in these figures. it is observed from this figure that the dielectric constant decreases with increase in frequency. The decrease in dielectric constant with frequency is exponential in nature and is analogous to Maxwell-Wagner interfacial type of polarization, which is in agreement with Cope's phenomenological theory. Now the dielectric loss. The variation of dielectric loss with frequency is also shown in this figure. Dielectric loss decreases with increase in frequency at lower frequency, which is because of decrease in polarization. At higher frequency, dielectric loss remains almost constant. The behavior of dielectric loss is similar to the dielectric constant. Lastly, the dielectric loss tangent. The variation of dielectric loss tangent with frequency is shown in these figures. It is evident from this figure that, like dielectric constant, dielectric loss tangents also decreases exponentially with increase of frequency and attains constant value of higher frequency. It is well known that there is a strong correlation between the conduction mechanism and dielectric behavior of ferrite. The conduction mechanism in the present series is considered as due to hopping of electrons between Fe2 plus and Fe3 plus ions and jumping of holes from between Ni2 plus and Ni3 plus in p-type ferrites. As such, when the hopping frequency nearly equals to that of the externally applied electric field, the maximum loss may be observed. Lastly, the conclusions from the experimental data obtained on the structural, electric and dielectric properties of Ni1 minus X CUX Fe2O4 leads to conclude the following. The formation of single phase cubic spinel structure of all the samples of NiCu spinel ferrite is confirmed from the sharp and well-defined intensity peak seen in X-ray diffraction pattern. The lattice constant determined from XRD data increases with increase in copper content X, which is understood from the difference in ionic radii of Ni2 plus and Cu2 plus ions. X-ray density decreases with increase in copper content X. The DC resistivity decreases with increase in temperature. Dielectric study shows the normal dielectric behavior of all the samples and strong influence of frequencies, which could be attributed to the Maxwell-Wagner polarization mechanisms. Thank you, sir.
Thank you very much, Bandari sir.
Thank you, sir.
If participants has any questions, they can ask. No, I think there is no any question. So we will proceed further. Thank you very much. Then next participant is Rushali Yerpude ma'am. Kage sir. Kage sir.
सर येस सर
येरपुडे मॅमचं आहे का पीपीटी
हो हो
असेल
आली पीपीटी ते मी हे करतो
ओके तर येरपुडे मॅम am I audible?
Yes, sir.
So now after displaying PPT, you can make your presentation.
मला करा Sir, I am showing that presentation. Wait for a minute.
Okay, ma'am, the PPT is now visible, so you can make your presentation now.
Welcome you all for today's presentation on the topic investigation of luminescence characteristics in Na14.95 minus X KX SO4 5F4Cl doped with copper phosphor, which was completed under the able guidance of Dr. K.B. Ghormare and Dr. S.J. Doble, RTMNU, Nagpur. Next. In the present work to synthesize efficient activated halosulfate host time-saving and wet chemical method, followed by study of its luminescence properties to explore its practice. CU plus exhibits responding to 3D10 to 3D. The presence of in the ultraviolet and visible range of the spectrum. CU plus doped phosphorus can be best replacement for highly expensive cerium or European doped blue emitting phosphorus. Next. This phosphor. Next. Next, please. This phosphor was synthesized by wet chemical route. 0.05 SO4 was proportion of 0.1. The did not match. No JS available for the unknown compound. The peak around 111200, which can be indexed to the copper JCPDS number 851326. Next. The excitation spectrum was monitored at 417 nanometer emission wavelength for 0.1 K2SO4 concentration and 0.05 mole% of copper to obtain broad peak at 355 nanometer. PL emission spectra at a high intensity broadband at 470 nanometer to 310. The PL intensity the first chromatic coordinates were found to be 0.1620 and 0.0732, which is in the blue range near the edge of color space. So the result suggests that phosphor is a promising candidate as a colored LED. Next. Thermoluminescence study was done for the phosphor. The phosphor was irradiated by gamma rays for dose of 500 gray with a dose rate. Previous, please. TL study. Previous slide. Please show the previous slide. Yes. The phosphor was irradiated by gamma rays for dose of 3.9 hour. TL glow curve comprises of two peaks positioned at 171 degrees Celsius and 249 degrees Celsius, indicating double trapping sites. The intensity of TL peaks increases with increase in K concentration. The trap parameters, namely order of kinetics, activation energy, frequency factor associated with the most intensive glow peak were determined by chain peak shape method using computerized glow curve deconvolution technique as given in the table. So the present phosphor follows second order kinetics with least value of figure of merit and can be used for dosimetry in ionizing radiation. Next. Next. Conclusion, the phosphor was synthesized by wet chemical route and as per the XRD pattern, it is a new phase. Photoluminescence of the synthesized material confirmed the incorporation of copper into the host material. And the CI chromatic coordinates were located in the blue region near the edge of the color space. Trapping parameters were determined by using chain peak shape method for the phosphor. And the phosphor can be promising aspirant for application as blue colored LED and may be quite suitable for use in docency of ionizing radiations. Next. Thank you.
Okay, thank you very much, ma'am,
Thank
for
you, sir.
presenting TL phosphor, Paracon TL phosphor. Now our next presenter is Ankush D. Deshmukh. So I request Ankush Deshmukh sir to present his work. Deshmukh sir, you can make your presentation now.
Okay. Population universality class with the afternoon one and I am just going to. Hello.
Yes, sir, you're audible.
Am I audible, sir?
Yes,
You are
sir.
audible, sir. You are audible, sir, and you can now share your presentation and you can make your presentation.
Hello.
Hello, you are audible, sir.
Hello. Good afternoon. I am Uncle Deshmukh. Hello.
Sir, you are audible. You can share your PPT or
Okay.
whatever it may be, PPT, PDF, or video.
From Department of Physics. Afternoon, Vanana. I am Uncle Deshmukh. Entitled Transition to Absorption in Contact Process on Multiplex Network.
Sir, excuse me, sir.
From Department of Physics, RTM Nagpur University. I am going to present the basics model. First one is advanced linear multiplex network. It is also known as.
Ankush sir,
in this
your
model,
PPT is not visible.
Hello. Hello, sir.
Your presentation is not visible, sir.
Visible.
You have to share that whatever you have, PPT or PDF, you have to share.
Okay.
Yes. Okay, it is visible now. Yes, it is visible. It is visible, sir. Yes, it is visible. It is visible, but something different is coming. Only icons are visible, sir. I think you are playing video, right? It is visible now. It is visible. You can increase your volume now.
Here, to present this model is
Sir, audio is not clear.
here we try for this one
Sir, your audio is not clear.
Please check your audio.
Sir, your audio is not clear. I think you are playing it from mobile.
We can actually say.
Hello. Ankush sir, am I audible to you? Hello, Ankush sir. Hello. I think network problem is there. हाँ सर, आवाज येत नाहीये का? Your audio is not clear. No? Is there any network issue? What we'll do, we'll try after some time. I think we should head to the next participant.
The same way, here also this side of
Kage sir, am I audible?
Yes sir, you're audible.
हे यांचं काहीतरी थोडंसं प्रॉब्लेम दिसतोय, नेटवर्क इश्यू दिसतोय, म्हणून ते ऑडिओ पण येत नाही व्यवस्थित.
हो हो.
तोपर्यंत एक काम करू, यांना नंतर घेऊ. टाइम वेस्ट करण्यापेक्षा दुसऱ्यांना आपण continue.
हो चालेल चालेल चालेल.
Okay. I think next participant is Dr. Arvind Sarode. Right. Ankush sir, we will try after some time. Okay.
Hello, sir.
Dr. Arvind Sarode.
Sir, I will present my presentation after 5 minutes, sir.
Yeah.
After this. Okay, sir.
Who is speaking? Sarode sir.
Hi, yeah, myself, Dr. Sarode. So I am uploading my PPT, sir. So I will present my presentation after 5 minutes, sir.
Okay. Then till now, then there is another participant. Samson Apparanti, right?
Okay.
Kage sir, make him presenter.
Okay.
Kage sir.
Yeah, I am making, sir.
I'm
I'm
with you.
making.
Samson of parenting is online.
Yeah.
I'm making him presented.
So, Samson sir, Dr. Samson sir, you can now make your presentation.
Okay. Everyone. I'm Oparati Samson Ikiola from Department of Physics, Faculty of Physical Science, from Nigeria. Sorry, am I audible?
You are audible, sir.
Yeah. I'm presenting synthesis and characterization of alternative insulating fluid for a transformer application. The transformer is a very vital and imperative equipment in our society, and with some lack of maintenance and improper management, we face a lot of power outage and breakdown of transformers. You can see from this diagram to the next diagram, the oil, the major importance of the oil is to separate, is to serve as an insulator between the primary terminals and the secondary terminal. However, since the inception, mineral oil has been used over time, and as a insulating oil. But due to environmental impact, it has caused a lot of damages to our environment, more than the importance. So we need an alternative insulating oil. So attention was placed on natural ester, and it was revealed that it possesses some unique properties which make them superior to mineral oil. But they have this green alternative have a kind of issues of high dielectric loss and high conductivity. So this work studies the effects of titanium oxide nanoparticle on the flash point, 4 points, and the viscosity. Although in our previous publication we have worked on how to reduce the dielectric loss and the conductivity of this natural ester, but little attention was placed on the physicochemical properties, that the flash point, the pour point, and the viscosity. The major function of this oil is to serve as insulator and a coolant, but majorly people place more attention on the electrical properties, but little attention was placed on cooling properties. So this work focused on the cooling properties of insulating oil, of insulating natural ester. This is the sample preparation. The crude palm kernel oil was prepared and it was purified using the Dastran and Dastran method. After the purification, the oil was transesterified using sodium, using result as a catalyst and mixed with methanol. So the oil was transesterified. After the transesterification, the nanoparticle was coated. The essence of the coating is to allow proper distribution of the proper suspension of the nanoparticle in the oil, because you know that the density of the nanoparticle is more than that of the oil. So there will be a kind of a sedimentation. So to prevent the sedimentation and functionalize it, to increase the to reduce the van der Waals attraction to the nanoparticle. So sample preparation procedure, the citric acid was used for deguming. After deguming, these are the necessary procedures for purification of the oil. After the purification of the oil was filtered using Workman number 1 and number 5. So immediately after the filtration, the oil was tested for acid value to know if transesterification will be done or acid esterification. So eventually, we did transesterification, and this is the separation. This is the separation, and the glycerol and the methyl ester at the top. So the glycerin was separated, and the methyl ester was washed with warm water. After the washing, functionalization of the nanoparticle was done, and nanofluid was prepared in the step of 0.2. It was prepared from 0.2 to 1 weight percent in the step of 0.2. After then, the characterization was done, viscosity, pour point, and the flash point was determined. Pour point, as we all know, that pour point is defined as the temperature at which crude oil, at which the particular temperature at which it loses fluidity. So the pour point was done according to the STM standard by heating up to 400 degrees C, after which it was transferred to the test jar. So from the test jar, the specimen was cooled at the rate of 1.5 degrees centigrade, and the flow characteristics of the specimen was examined by site. So the particular point at which it loses fluidity, the lowest temperature was taken as the pour point. Flash point. Flash point was also determined. It was according to what we know, flash point is at the fluid hazard of the ester. So the flash point was determined experimentally, also according to the ASTM standard. So the film was put on the face, and the temperature at which the ignition was recorded at the viscosity. Now, the viscosity is very, very important when you are talking about the cooling of a power transformer, because this oil is the one that serves as a coolant. So we need oil with low viscosity as much as possible to have a kind of proper circulation in the oil, which is also a function of Reynolds number. So the essence of the esterification to remove the glycerol was done to remove the glycerin. The glycerin is the one that makes the purified oil to have high viscosity. So the viscosity was done, and it was done using an RSD viscometer. So these are the results. It can be observed from the graph that addition of nanoparticle increases from figure 1. Addition of nanoparticle increases the pour point of the methyl ester, because it's just like adding a kind of a friction. So when you add it together to it, the nanoparticle form a solid liquid interface. So when it is subjected to low temperature, a kind of solidification, so the oil loses its fluidity. The flash point is, according to what I said earlier, the flash point is the point at which the flame of the ester form a kind of ignition. So when the nanoparticle is added, the nanoparticle attach themselves to the molecule of the oil. So when it is subjected to high temperature, the dissociation of the molecule of the oil is not. It takes time for the dissociation of the molecule of the oil to occur, so which increases the flash point of the methyl ester.
The next one, the figure 3. Actually, it was noticed that at room temperature, when we check the degree temperature, at room temperature, when the nanoparticle is added, the viscosity of the nanofluid slightly increased due to the fact that the nanoparticle, which is assumed to be a nanoparticle in the solid material, cause a kind of internal friction with the spindle of the viscometer. The increment in the concentration of the nanoparticle caused a slight increase in viscosity of the ester. However, the 1%, the 1 weight percent of the nanofluid still have a considerable viscosity more than that of the mineral oil. What point of nanofluid was observed to have increased by 81% for 1 weight percent. This reaction
Excuse me, Operanti sir. Try to conclude within 1 minute.
The flash point was increased, the pour point was increased. Actually, its increment in the viscosity was increased according to what is shown in the PowerPoint. Characteristics of oil reveal that synthesized nanofluid has a promising property that will make it to serve as a better replacement for mineral. The value obtained compared to the standard insulating was observed the flash point and the viscosity far better. The viscosity and the flash point was far better than that of the mineral oil. So it shows that it can be a replacement for mineral insulating oil. Although the pour point was found to increase, which is not a good result, but the oil can still be high temperature and for a low temperature region. Thank you for your time and attention. Thank you so much.
Thank you, Dr. Samson Operanti, for sharing your work on synthesis of nanofluids and its application as insulating oil. So thank you once again. Now, Arvind Sarode. Now I call upon Dr. Arvind Sarode for presenting his work.
Yes, sir. Good afternoon, sir.
Kage sir, make him presenter. So, Dr. Sarode sir, you are now the presenter and now you can make your presentation.
Yeah, sir. Sir, I have shared my PPTs with Kage sir. Hello.
Okay, sir. Kage sir.
Yeah, just a minute.
Okay.
Sir, we have not got his presentation.
Sir, I sent my presentation to your WhatsApp mail, sir.
WhatsApp, okay.
Yes, sir. Yeah.
Yes, sir. Now it take time to open.
Okay, sir.
Okay. Mumode sir, meanwhile, we can take other participant because it takes time.
Okay, sir. So we have another participants. 1 minute. Dr. Sanjay Bagde. Dr. Sanjay Bagde, I think. Yes. Kage sir, he is in attendee. Sanjay Bagde sir. So take him to panelist and make him presenter.
He is now panelist.
Yeah, you can make him presenter now. Sanjay Bagde sir.
Yes, sir.
You can make your presentation now. Hello, you are
Okay, sir.
audible, sir. You can make your presentation.
Yes, sir. But my slide. Please display my slide, sir.
It is with us or?
Yes, yes. I have sent it to Kage, sir.
Sir, we have not received that email.
Sir, I have sent it to the mail gug.registrar. Hello.
Hello, sir. Sir, that is not official mail of the conference.
Sir, can you tell me the mail then?
Okay, sir. It is CONIAPS26physics@gmail.com.
Okay, sir. I will try to send it.
Sir, till then we'll take another participants. We have with us Dr. R.B. Kawade. Right. Kawade sir, am I audible? Kage sir. Kage sir. Kage sir.
हॅलो सर.
तोपर्यंत आहे ना कवाडे सर आहेत त्यांना प्रेझेंट करायला सांगूया.
हो हो.
ठीक आहे. ते अटेंडी मध्ये पण मला वाटते ते लॅपटॉपवर आहेत प्रेझेंट.
त्यांना प्रेझेंटर करूया.
हा, तर त्यांना प्रेझेंटर करा. अटेंडी मध्ये आहेत ते.
आवाज काय येतो एवढा जास्त?
So now I call upon Ramdas Kawade sir, Dr. Ramdas Kawade to make his presentation. Kawade sir. Kawade sir, am I audible?
Unmute.
You can unmute yourself.
Yeah, school.
Am I audible, sir? Am I audible?
Yeah, you are audible, sir.
Hello.
Now you are audible, sir. You can make your presentation now. You share your PPT. You are the presenter now.
Am I audible, sir? Is my PPT seeing, sir? Hello.
PPT is not visible, sir.
Then not getting the option of sharing the PPT. How to share? Sharing option is not getting. Start video. Share. Okay.
There is one sharing tab. So you just press on the sharing tab.
Hello, sir.
It is coming, sir, now. You can now start your presentation.
PPT is visible now, sir.
It is visible, but it means background is totally black.
Black. Sir. Is PPT seeing, sir, or not?
It is shared, but nothing is visible. Means the background is totally black.
Sharing is start. Option to the front. Stop sharing. अभी दिख रहा है क्या सर कुछ नहीं
नाही दिसत आहे.
अभी क्या करें शेअर तो
नेक्स्ट करून बघा दिसतोय काय तर.
मला तर पूर्ण दिसतंय ते.
एकदा काम करा, त्याला स्टॉप करा आणि परत एकदा शेअर करा.
मोबाइल पे कर सकते हैं सर मैं हेलो सर
If you are comfortable with mobile, then go for mobile. लॅपटॉप वर तसं इझी आहे.
पण ते आता शेअर व्हायना ना ऑप्शन नवीन असल्यामुळे शेअरिंग
शेअर करा आणि तुम्ही कुठलं शेअर केलं काय माहिती.
नाही ना पीपीटी मला दिसते शेअर केल्यानंतर तुमच्याकडे ब्लॅक दिसायला लागले.
इथे ब्लॅक दिसतोय.
मोबाईलवर तर ऑप्शनच येत नाही शेअरिंगचं तर
सर तुमचा व्हिडिओ दिसतोय. त्याच्या साईडलाच ते असेल.
Hello, sir.
Kawade sir, do one thing. You can send your PPT to our CONIAPS official mail. Okay. We will play from our end and then you can present. So till now, without wasting much time, we will move towards our another participant because we have limited time, right?
Okay.
So better way you mail us, then we will play. Okay. So now I think Sarode sir is ready with his
Yeah.
presentation.
Yes, sir.
So I request Kage sir to play his PPT and I will request Dr. Sarode sir to make his presentation.
Okay, sir. Sure. Hello.
As you are audible, now you can make your presentation.
Okay, sir. Thank you. Good afternoon to one and all, the respected chair of this session. Dear friends,
Kage sir, first
we
slide.
come across different solvents. Yeah, first law. Sir, myself, Dr. Sarode Arvind Vishwanath from School of Physical Sciences, Swami Raman Tirth Marathoda University. And today I am going to talk on my topic, effect of low temperature on the structural behavior of DMSO using dielectric spectroscopy. Next. Okay, dear friends, as a researcher, everybody, we come across different solvents such as water, acetone, dimethyl sulfoxide, dimethyl etc. So among these, DMSO, in spite of its freezing point at 19 degrees centigrade, does not melt below its freezing point. And this property compelled me to study its low temperature behavior using dielectric spectroscopy. We are well aware of the structure of a DMSO, which is shown over here in the first figure. According to Shikata et al., published in his paper in Physical Chemistry, Chemical Physics, Communication, in the year 2011, DMSO at room temperature, the dissociation of DMSO dimers takes place into monomers. Next slide. Simulation that many possible conformations such as dimers, trimers, tetramers, etc. are possible for DMSO and concluded that the trimers are the most stable conformers of DMSO in pure liquid phase. Next. Therefore, these studies attracted me to see and validate the structural conformation of DMSO in liquid state below its freezing point. And so my aim of this present work is to study the low temperature dynamics of dimethyl sulfoxide through dielectric spectroscopy. Using time domain reflectometers, I have used in the range frequency range 10 megahertz to 50 gigahertz, and in the temperature region of 298.15 Kelvin to 273.15 Kelvin. And through this, I have studied dielectric properties such as static permittivity, static dielectric constant, relaxation time, dipole moment. Along with, I have corroborated these results with the thermodynamical parameters such as enthalpy of activation, entropy of activation, and free energy of activation. Next slide. Next slide. So this is the instrument I have used along with the block diagram. I am not going to go much detail in the experimental section. So next slide. Next slide, please. Hello, sir. Next slide. Okay. So with the help of that time domain spectrometer, I could obtain the spectra of dimethyl sulfoxide at different temperatures, which is shown over here at right from 298 means room temperature below to 0 degree centigrade. And using this expression, I could get dielectric permittivity and dielectric loss for the studied sample. Next. To get the more clarity, I have shown the same spectra at only two different temperatures, namely room temperature and at 0 degree centigrade. So as we go towards a lower temperature, clearly we can see two relaxation peaks, one at a lower frequency and another at a higher frequency, which is further analyzed using Debye model. Next. So this is the variation we could obtain so far as the dielectric parameters, means static dielectric constant is concerned. So for two frequency processes, means one is a principal relaxation and another is the high frequency response. So static dielectric constant varies and increases towards lower temperature, and the same happens with the high frequency relaxation process. So both the relaxation modes observed are distinctly from different molecular origins. The first relaxation means a principal relaxation for major relaxation mode is not simply attributed to the contribution of freely rotating monomeric DMSO molecules. Also, the increase in the magnitude of second dielectric constant, means the high frequency dielectric constant towards a lower temperature, it results from increase in the concentration of monomers due to dissociation of the dimers. Next slide. Similarly, we could clearly observe about the variation in relaxation time with the temperature. For both the relaxation time, particularly the major relaxation mode, means principal relaxation mode, is assigned to the dynamics of molecular association, such as dimers, and the minor mode is assigned to the monomers, and this monomer increase in the value of means both T1, tau1 and tau2. So this tau1 and tau2 increases, it is mainly because of the hindrance offered by dimers and monomers respectively. Next slide, sir. We have also obtained dipole moment for the DMSO at a different temperature. So the variation of dipole moments we can see. So linear increase in the dipole moment we can see, and this linear increase in the dipole moment, it is because of the structural alignment of DMSO dimer, such that the effective dipole moment increases towards lower temperature. Next slide. We have also observed and obtained thermodynamic parameters for dimethyl sulfoxide, means free energy of activation and entropy of activation. So you can clearly see the variation of free energy of activation, which is almost constant for the principal relaxation mode and slightly increases towards the lower temperature. Entropy of activation, if you see, means the red color line with symbols. So it is slightly increases with lowering in temperature, which further suggests that the conformation or the structural alignment is not so well ordered, means it more disorderness is here towards the lower temperature. Next slide. We have also obtained the free energy of activation and entropy of activation for the high frequency process also. The variation you can see clearly means the free energy of activation, which is increased very means minorly increases towards the lower temperature, but here entropy of activation, it is linearly increasing, which also suggests that the strong alignment and a strong association of dimers towards lower temperature is possible. Next. Slide, please. So these are my findings, and finally we can conclude that for DMSO, two relaxation processes we could observe for all the studied temperatures, particularly at room temperature. The dissociation of a DMSO dimer is the major dielectric relaxation process at the lower frequency side, while the relaxation of monomers of DMSO is a minor mode, which we can see at a higher frequency side. Both the relaxation modes observed are from distinct molecular origins. Major relaxation mode is not simply attributed to the contribution of freely rotating monomeric DMSO molecules. Towards lower temperature, molecular association of dimer is more, which results in increase the value of effective dipole moment. Increase in the magnitude of high frequency static dielectric constant and relaxation time is due to increase in the concentration of monomers and hindrance offered for the rotational motion respectively. And finally, these results we observed, they are well supported by the obtained thermodynamical parameters such as free energy of activation, enthalpy of activation, entropy of activation for both the relaxation process. Next slide. So these are my findings for dimethyl sulfoxide. Thank you, sir. If any questions are there, we are most welcome.
So
hello?
if yeah, thank you very much, sir. Now, if anybody has any question, you can type your questions in chat box. I think there is no question. So now, by considering the time constraint, we are heading towards our new means other participants. Now, I'll call upon Dr. Sanjay Bhagade to make his presentation. I think he is in attendees list. So yeah. So I request Dr. Sanjay Bhagade sir to make his presentation now.
Sir, please share
Kage
my
sir,
screen.
Yeah. Kage sir, तुम्ही share करताय का?
I'm sharing.
Okay, sir. You can make your presentation now, sir. And
Okay, sir. Can I
give a
start?
limit of 5 minutes. Yeah.
Okay, sir. Okay, sir. So good afternoon to one and all. Respected chairman of this session, I am Sanjay Bagade from Bajaj College of Science, Varda, and I will be making a presentation on the topic estimation of dipole moment and dielectric behavior of binary mixtures containing certain amides dissolved in non-polar liquid hexane. So next slide. Sir, next slide, please, sir. So what is the importance of this study? The study of amide is important because amides are found in most of the biological applications. And what is more important about amides is that they possess very high dielectric constant. Now in our present study, a system of organic binary mixture which contains various polar amides, which I have noted by the symbol B here. I have denoted by A, and this mixture is studied for their dielectric response and presence of low electric field. Important because the dielectric studies or dielectric behavior study of a particular mixture, it gives us the knowledge about the kinematics that is going on in that liquid, the variations that are going on, and the chemical knowledge can also be gained from that studies. So this binary liquid mixture, it contains amides like formamide, acetamide, N-methyl acetamide, N-dimethyl acetamide, acetanilide dissolved in non-polar solvent hexane. And this dielectric behavior study is studied by computing the static dipole moment from the knowledge of static relative permittivity, which I have denoted by epsilon 0 AB, and high frequency permittivity, which I have denoted by epsilon infinity AB. And this is done for different weight fractions of the mixture of the solute at 30 degrees centigrade temperature. Sir, next slide, please. Sir, next slide. In this study, the Debye model of polar liquid, it is used for the study. And why the Debye model is used? Because it is true only at lower frequency. At higher frequency, this model fails. So we are making this study at lower static electric field. So the theoretical formulation in this particular study, according to that Debye theory, the formula which I am going to use is the dipole moment nu s. This is the static low frequency dipole moment. Nu s is equal to 27 epsilon 0 mb kb into t divided by n rho a into p1 raised to the power 1 by 2. All the symbols, which are all the parameters which are used here, they are having their relevant meanings or meanings which we are used in our daily practical applications. The important thing here is P1. So next slide please. Here P1, it is the slope of the curve which is drawn between XAB and WB for very small values of WB, and this curve is shown in the figure 1. Now here XAB, this is static experimental parameter which can be calculated by using the formula which I have shown here, and WB is the weight fraction of the polar solid. So next slide. So these are the various calculations which I have made. On the left hand side, we can see the mixture, binary mixture which I have taken, and then second column is the weight fraction, and the extreme right column, that is the static experimental parameter XAB, and we are going to draw a graph between static experimental parameter XAB on the y-axis and the weight fraction WB of the solute on the x-axis. So next slide. So this is the graph which we have obtained. Now in this graph, there a very similar nature of the graph is seen here. but that is not of so much importance to us. What we are going to find from this graph is the slope of this graph, and that slope is the P1, parameter P1, which we have used in that formula. So different binary mixtures is having different nature of the graph, and we are getting different slopes for different binary mixtures. So next slide. So sir, on the basis of these calculations, by putting the value of P1, coefficient P1 in the first column, it is nothing but the slope of that graph. For different binary mixtures, it is different. And by using this slope, value of slope of graph, we have calculated the static dipole moment nu s, which I have shown in the extreme right table, column. Now, and the rest of the two columns, one is nu b. This is reported dipole moment from conductivity measured experimentally by other researchers, and the theoretical dipole moment, this can be calculated from the bond angle measurements for different solutes mixed in this solvent. Now what we observe from this table is that the values, they are not similar, but they are nearly same. Values are in close vicinity of each other, though they are not same, but they are very close to each other. So next slide. So as in result and discussion, I can just state that the static dipole moment nu s, which we have calculated, they were found to be directly proportional to square root of the slope P1 of the XAB WB curves. The almost similar nature of the curve indicates similar magnitude of slope of the graph, which indicates a similar polarity of the solute molecules. Higher values of static dipole moment nu s for formamide and N-methyl acetamide. It may be due to slightly higher values of the slope P1, and higher values of nu s for formamide and N-methyl acetamide indicate a solute-solute dimer molecular association through hydrogen bonding in hexane with increasing concentration. So next slide. Fifth point is that the hydrogen bonding causes the alignment of polar amide molecules to increase the polarization, and hence the dielectric properties also increases, and also we observe an increase in dipole moment. Now in all those three tables which I have shown, a good agreement is observed between the calculated static dipole moment nu s, reported dipole moment nu b from conductivity measurement techniques, and nu t from the dipole moment from the bond angle. I have mentioned earlier that there is a slight variation. Now this slight variation, it may be due to the discrepancies, and it may be due to the effect of the static applied low frequency electric field. So next slide. So in the conclusion, sir.
Try to conclude within 1 minute.
Sir, this is last slide.
Okay.
So in conclusion, I would just like to state that the primary and secondary amides show a solute-solute dimer interaction through hydrogen bonding in non-polar solvent hexane. The intramolecular charge distribution introduced due to the dipole adjacent to the polar group is responsible for the dipole moment and dielectric behavior. Now also we can conclude that inductive, mesomeric and electromeric effect are responsible for the changes in bond angle, and they impart a bond moment, and hence a dielectric response is observed. So next slide. So in conclusion, the Debye theory of polar molecules can successfully explain the polarization and dipole moment of dilute solution of polar non-polar organic mixture of certain amides dissolved in hexane, which is observed by nearly correct values of calculated values of dipole moment nu s. So last slide. So these are the references. That's all from my side. Have a nice day.
Thank you very much.
Have a nice day, sir.
Thank you very much.
Okay, sir.
Now we are heading towards our next participant. Now I will call upon Dr. Komal Kabra. Ma'am, am I audible?
Yes, sir.
Yeah, you can now make your presentation.
Yeah, my PPT is with Kage, sir. Okay. Good evening, one and all. Myself, Kobra from Swami Ramanand Tirth University. The topic of my today's presentation is study of molecular interaction in E-satin and DMSO mixture using dielectric spectroscopy. Next slide. Aims and objective of my study are: I have studied dielectric constant and relaxation time of E-satin with the DMSO, as well as I have studied thermodynamic properties such as entropy, enthalpy, and free energy with the help of time domain reflectometry in the temperature range of 0 degree centigrade to 25 degree centigrade using at 10 megahertz to 50 gigahertz frequency. Next slide, please. Here I have used the instrument time domain reflectometry, which works in the range of 10 to 50 gigahertz. It is mainly consist of three parts, that is sampling oscilloscope, sampling module, and temperature controller system. The main function of sampling module is to generate the step pulse, and the generated step pulse were carried out with the help of coaxial cable, which is having resistance around 50 ohm. The generated step pulse then interact with sample which is kept in the temperature controller system, and the reflected response then again sent back to the sent back through the coaxial cable to the sampling oscilloscope, where the data is stored, and with the help of USB or any hardware device we can collect the data for our further analysis. For further analysis, we use different softwares like Turbo Basic, Origin, and this is the original setup in our laboratory, which is given in the third figure. Next slide, sir. These are the waveforms which we see on sampling oscilloscope, that is R1 of t and Rx of t. R1 of t is without sample and Rx of t is with sample. These pulses are added and subtracted, which is denoted, that is added pulse is denoted by red symbol and the subtracted pulse is denoted by black line. And next slide, sir. We found these pulses in we have to change the pulses in frequency domain, so we use Fourier transformation to convert the P of t and Q of t into P of omega and Q of omega. Next slide, sir. Now here we are using dielectric Herveliak-Nizami equation for calculating dielectric constant and relaxation time. All the values, all the explanation of the symbols is given below, that is epsilon star is complex permittivity, which we are going to found, and alpha and beta are distribution parameter. Depends on the distribution parameters, we can decide the means fitting model, in which model we have to fit our data. Next slide. Now there are three models: Debye, Kolkol, and Cole-Davidson model. Here you can see the change in the shapes. In Debye model, you found perfect semicircle. In Kolkol model, it is also semicircle, but the center of the semicircle lies below the x-axis. And in Cole-Davidson model, you get skewed like structure. Next slide, sir. Again, we have calculated thermodynamic property with the help of Eyring's rate equation, that is entropy, enthalpy, and free energy we have calculated using this equation. Next. Now here, this is the esatin molecule which we have used for our study, and the solvent is DMSO. The molecular formula is given here, C8H5NO2 is for esatin, and esatin have a number of advantages or uses in our day-to-day life. Next slide. Next. Now, this is the dielectric constant. Here you can see that variation of dielectric constant as a function of concentration as well as temperature. Here dielectric constant was observed to be increases at low temperature towards higher concentration, and then it starts decreasing towards higher concentration, higher temperature. At lower concentration, it is 0.012, which is indicated by black symbols. That is, at lower concentration, dielectric constant was found to be in between 50 to 57. If we further increase the concentration of esatin into DMSO, then there is sudden increase in the dielectric constant, which is shown by blue line. But for increase in dielectric, but for further increase in the concentration, again dielectric constant goes on increasing. This is because at lower concentration of esatin, dipole moment of esatin are aligned parallelly to DMSO, so that the resultant dipole moment increases, and there may be association between solute and solvent molecules. Next slide, sir. Now, relaxation time. Relaxation time found to be increasing with increasing concentration, but it found to be decreasing towards higher temperature, which is shown in figure. For higher temperature, the relaxation time found to be decreasing. At lower temperature and higher concentration, it found to be higher. And even for higher concentration, that is 0.046, relaxation time found to be very high. We can say that the increase in relaxation time with increasing concentration of esatin, that there is less probability of reorientation at higher concentration and lower temperature. This may be due to the large hindrance to the reorientation of esatin, yes, in the surrounding of DMSO molecule.
Excuse me, ma'am. Try to conclude within 1 minute.
Okay, sir. Or we say that there is a less rotation of esatin molecule in the vicinity of DMSO molecule. Next slide, sir. Now, in case of free energy, the free energy of activation, that is delta F, is measured at low and high concentration in the temperature range of 25 to 0 degrees centigrade. And here also we found that at low temperature, free energy was found to be more, and it decreases up to 15 degree, that is 288.15 Kelvin. If we further increase the temperature, free energy starts increasing. This increase in the values of free energy with rise in temperature may be due to the induced intermolecular hydrogen bond between esatin and DMSO molecule. That is, the bond formation increases the thermal agitation, and the dipole require more energy in order to attain equilibrium with the applied field. Next and last slide. Here we have calculated entropy. Entropy is nothing but the for measuring the orderness or disorderness of the system. In this case, we found that the entropy of the studied systems are positive. That is, they are less ordered systems, and we can conclude that values of entropies indicates that there is a dipole-dipole association. That is, the molecules of esatin are anti-parallelly aligned. Next slide. I am very much thankful to my research guide, Dr. Sarode sir, for his guidance, and all my research colleagues for their cooperation. And thank you to the team of this conference. Next slide. Thank you, sir.
Thank you very much, ma'am, for sharing your research work. Now we have with us Dr. R.B. Kawade. Kawade sir, are you ready? Kawade sir, are you there? Kage sir?
Hello.
Sir, wait a minute. I am trying to open his PPT.
नाही, मी ओपन केलेला आहे. मला तुम्ही करू शकता प्रेझेंटर.
हा ठीक आहे.
ओके.
मोठे सर.
Kawade sir, are you there?
Yes, sir.
So I am sharing your PPT now.
Okay, sir.
Is it visible now?
Yes.
So now you can make your presentation, sir.
Good afternoon, one and all. Hello. Am I audible?
You are audible, sir.
Yes.
Yeah, you are audible, sir. Continue.
Good afternoon, everyone. In the 26th International Conference, myself, Dr. R.B. Kaude, topic of my presentation is influence of copper ions. Next slide, sir. Plan of my presentation. Next slide, sir. Hello, sir. Plan of my presentation is preparation method, experimental technique, result, discussion, and conclusion. Next, please. Introduction. Ferrites are complex magnetic oxide that contains ferric oxide Fe2O3 as their main component along with metal oxide. Ferrite possesses both electrical and magnetic properties and hence they are commercially important material. On the basis of crystallographic aspect, ferrites are classified into three major types, that is cubic ferrite of spinel type, cubic ferrite of ferrite. Slide. Method generally are prepared by ceramic method. There are various though these methods yield nanoparticles, the importance of conventional ceramic method still exists. There are various types of methods to prepare the ferrite: sol-gel method, precursor method, combustion synthesis, spray pyrolysis technique, chemical bath deposition technique, wet chemical co-precipitation technique. Next slide, sir. Next, please. Next slide. Next, this is what the method flowchart of ceramic technique. Now prepared the sample. Next slide. Next, please. Present work, that is the prepared samples are examined by the techniques, that is XRD technique, cation distribution, and dielectric properties. Next. Results and discussion. In the present work, copper substituted nickel Fe2O4 system is prepared by ceramic technique and characterized as follows. Next slide, sir. Next slide. These are the XRDs of all the samples, and this table shows the lattice constant, X-ray density, bulk density, particle size of all the samples. It is observed from the table that the lattice constant increases with increase in copper concentration. This is because of higher radius of the copper cations as compared to the nickel. Next, cation distribution. There are various methods to do the cation distribution. In the present work, X-ray diffraction method is used to make the cation distribution. Other methods are magnetic. That is IHKL. The intensity of all the planes is calculated by using this Berger formula, in which F is structure factor and LP is the Lorentz polarization factor and P is the Next slide. X-ray intensity ratios of the system is shown. From the XRD data, intensity ratios of typical planes 220, 400, 440 and 220 is calculated, and these ratios of intensity are compared with the observed intensity ratios factor, that is observed and calculated intensity ratios are minimized and cation distribution is calculated, which is shown in the table. From this table, it is observed that the cations nickel occupy only B side, whereas copper and Fe ions occupy both A and B sides. The calculated cation distribution is shown here. Analysis of dielectric properties. From this graph, it is observed that substitution of copper ion increases the dielectric parameters, that dielectric constant, dielectric loss, and dielectric constant. Frequency values are very high with increasing frequency.
Sir, you are not audible.
And 10,000 kilo. 1 megahertz. Next slide, please. Then cation distribution calculations suggest that Ni2 plus ion occupy B side, whereas Cu2 plus ion and Fe3 plus ion occupies both A and B side. The value of the parameters, that is epsilon dash, epsilon double dash, and are high at low frequency but decreases with increasing frequency, and substitution of copper cations increases the dielectric parameters. Thank you, sir. Thank you.
Okay, thank you very much, sir. Now I think all the participants from today's oral presentation list are, I think, over. Those who were present. Now, I think, let us see any other participants are left or not.
Sirs, I think all the participants have done their presentation for today's session.
Yes. I
Yeah.
think Sanjay Nagdevte sir is there. You can. He is in attendee. You can take
Okay.
him
Okay.
to.
Yeah. We shall make him presenter.
Yeah. Only one participant is there.
एक शिल्लक आहे. Sir, we are unable to make him a panelist.
Okay. What we can do now?
Hello, Kage sir and Chagan.
हाँ सर.
पार्टिसिपेंट जर झाले असतील, so
Almost
you can
completed.
end up with the conclude with feedback report.
Okay.
And that vote of thanks will be given by Kage sir.
Feedback,
Yes,
online
sir.
feedback.
No, if any one of the participant is there, Nandi or
Okay.
something like
Okay.
that.
Okay.
So
Okay.
one or
So-
two participants, they will give the feedback. Then Mugmore sir will give the report of the international conference.
Okay, sir. So we shall proceed in this way, sir. Okay.
Yeah, and you give the vote of thanks.
Yes. Definitely, sir.
Yeah.
Okay. So on behalf of this Gondwana University and IIPS, I thank Dr. Mumude for chairing this session. He chaired this session very wonderfully and nicely. And now I request to the participants, if they wish to give feedback, they can raise their hand
पहिले
in the
खाकी
chat
धुवून माग
box.
नाही तर विनोदला ते बाकी काही धुण्यापेक्षा अजून 8 दिवसांना अजून त्याला बोलावून धुता येते आवाज
So if there are if anybody interested, please they may give the feedback for this conference. Yes, Sanand sir, you may proceed, sir.
Kage sir. Hello.
Sir, yes, sir.
That Nagdevte sir just called me, and if we can make him presenter, then.
So we tried, but it is not possible because to make him presenter.
No, there is price. We will from recording we can clear it. Pandey sir is joined before half an hour.
Okay, sir.
Yeah, so to
PNP.
start the program. Yeah.
Okay. PNP is the Pandey sir?
PN Pandey sir. Yeah.
Okay.
He is also
Kage sir.
panelist.
Okay, he is now panelist.
You
Kage sir will
you present the report, then Pandey sir will talk. So how many minutes you will take for report?
1 minute, sir. Okay.
No, report.
Report reading, na? Only 1 minute.
1 minute,
Only
na?
1 minute.
Okay.
Yeah.
So you just report and then ask for Pandey sir to give his feedback.
Okay.
Now may I call Dr. Mumude to present the report of this conference of IIPS. Please, Mumude sir, please read the report.
Yes, sir. Thank you very much, Kage sir. So, very good afternoon to all the dignitaries and participants present in this valedictory function of 26th International Conference on Advances in Physics. From last 3 days, we are together on this online platform to discuss and share the recent advances in and ideas in the field of physics. Now, here I am presenting a brief report of this conference. So, by considering the what you can say coronavirus pandemic, this online conference, international conference, was organized by Gondwana University, Gadchiroli, in collaboration with International Academy of Physical Sciences, Prayagraj, during the 18th to 20th December 2020. So, in view of convenience, CONIAPS 26 is being organized online at 11 different universities in India simultaneously, and this international conference was one of them. The online platform used for conducting this conference are WebEx and YouTube Live. The main focus of this conference was on the latest advances in physics and fundamental areas of applications, with particular emphasis on emerging trends. The registration process for this conference was carried out online, and 405, that means 4,505 participants were registered for this event from India and abroad. The inaugural function of the conference was held on 18th December 2020 at 9:30 a.m. For this function, Dr. I.S. Mohurle, convener of the conference, welcomed the dignitaries and all the participants. Professor Srinivasa Varkhedi, Chief Patron and Honorable Vice Chancellor of Gondwana University, Gadchiroli, inaugurated the conference and delivered presidential address. Professor P.K. Bajpai, Vice President IAPS, and Professor P.N. Pandey, General Secretary IAPS, were present as a chief guest, and they expressed their views about IAPS and this conference. Professor T. Kumar, Honorable Vice Chancellor, Guru Jambeshwar University, Hisar, was present as a chief guest, and he delivered keynote address. On the first day, that is on 18th December 2020, 2 technical sessions were conducted, in which 3 invited talks were delivered. First technical session was chaired by Professor Aparna Dikshit, PSIT Kanpur. Professor Kamlesh Balani from IIT Kanpur delivered talk on fascinating paradigm of advanced materials. The second talk was delivered by Professor R.C. Tiwari, Mizoram University, Aizawl, on prevention aspect of health hazards due to X-ray radiation for the health workers, patients, and to general public. The second technical session was chaired by Professor B.M. Bahirwar, Principal, Guru Nanak Science College, Ballarpur. In the second technical session, Professor S.K. Omanwar from Sant Gadge Baba Amravati University, Amravati, talked on challenges and opportunities in luminescent materials, special reference to development of spectral converters. The third session was dedicated for the oral presentation, and it was chaired by Professor Dr. R.M. Thombre, Chairman, Board of Studies in Physics, Gondwana University, Gadchiroli. On the second day of the conference, that is on 19th December 2020, the first technical session was chaired by Professor Ajay Lad, Amalokchan Mahavidyalaya, Yavatmal. The first technical talk of this session was delivered by Professor Michael from Linköping University, Sweden. In his talk, he talked about advances in physics as a facilitator of innovations. The second talk was second talk of the session was delivered by Professor Alok Shukla, NIT Mizoram, Aizawl. He spoke on the topic studies on La substitution at the Fe site of bismuth ferrite multiferroics. The second technical session was chaired by Dr. S.B. Revatkar, Dean Faculty of Science and Technology, Gondwana University, Gadchiroli. Professor Sanjay Dhobde, RTM Nagpur University, Nagpur, delivered the first talk of the session, in which he talked on color tunable rare earth activated phosphors for solid state lighting. The second talk of the session was delivered by Professor Anurag Mishra, DAE, Mumbai, on applications of particle accelerator for me, you, and everybody. The third session of the day was chaired by Professor R.G. Atram, Director, Institute of Science, Nagpur. In this session, Professor Abhay Kumar Singh, BHU Varanasi, talked on space weather, its causes and consequences. The fourth session was again dedicated to oral presentations of contributed papers by participants, which was chaired by Dr. Chhagan Mungmode. Today, on the third day of the conference, the first technical session was chaired by Professor S.C. Gedam, KZS Science College, Kalmeshwar. In first technical talk of the session, Professor Michael from the Linköping University, Sweden, spoke on carbon as materials for new research avenues. The second talk of the session was delivered by Professor Muhammad Imran Asgar, Aalto University, Finland, where he talked about progress in ceramics, nanocomposite, fuel cell, research and challenges. The third talk was delivered by Professor Sri Ganesh Prabhu, TIFR, Mumbai. He talked on challenges and future trends in terahertz spectroscopy. The second technical session of the day was chaired by Dr. D.H. Gane, NS College, Brahmapuri. In this session, first technical talk was delivered by Professor Nilu Suryani from Udayana University, Bali, Indonesia, and she talked on sustainable development model in Bali, Indonesia. The second technical talk was delivered by Professor Kishore Revatkar, Dr. Ambedkar College, Nagpur, on scientific challenges and achievements of 21st century, a perspective. Professor, okay. Now the third session was again dedicated to oral presentation of the contributed papers by participants. Now for this conference, total 65 abstracts were received for the oral presentation, and we have also received some papers which are now planned to publish in the Scopus Index Journal. Now for this valedictory function, we have Professor P.N. Pandey sir, General Secretary of IAPS, present at this event as a chief guest. Mr. Sandeep Kage sir, Organizing Secretary of the conference, anchored this international conference. Dr. Ishwar Mohurle, ex-registrar, Gondwana University, Gadchiroli, worked as a convener. Mr. Sandeep Kage worked as a organizing secretary. Dr. Chhagan Mungmode and Dr. Vishal Panse worked as joint secretary for the successful organization of this event. Dr. Devdatta Tare, Mr. Pramod Borkar, Mr. Krishna Devikar, Mr. Chute, they worked as a member of technical committee. With this, I stop myself here. Over to Kage sir.
Thank you very much, sir. Now I request General Secretary IAPS, Professor P.N. Pandey sir, to deliver his talk. Professor P.N. Pandey sir.
Pandey sir. Hello.
Can you hear me?
Yes, sir. Yes, sir. Sir, you are requested to deliver the presidential address, sir. Please, sir.
Thank you. Honorable Vice Chancellor, Ghana University, convener, organizing secretary, other members of organizing committee, speakers, honorable speakers, and researchers, friends. Good evening to all of you. First of all, I render my apology for not joining for much time in inaugural ceremony of CONIAPS 26 at Gondwana University. Especially to the convener, Dr. This This happened due to my PG schedule at the conferences under the umbrella of CONIAPS 26 at different universities. You are aware that CONIAPS 26 was to be held at Mahatma Gandhi University for time, Kerala, but due to COVID-19 pandemic, we had to change our strategy and decided to put it online at 11 centers of 10 reputed universities in 9 states of India. When I talked to Dr. Play, this conference, he has said yes. He said yes, we will do. I was eager to organize a conference of the academy in Maharashtra because last year was silver jubilee year of the academy, and mark its silver jubilee, decided to hold conferences in most of the states of India, and started from Jammu Kashmir. We went to extreme south, Kerala, and then other states, taking to northeast. Covered almost all states, and 29 conferences were held. But at that time, conference in Maharashtra could. So I was interested that at least it should be held at this time. And I am thankful to Dr. Mahurle who did this job, and he organized it in a very good manner. I didn't expect it that so many centers and so many participants will be there. But I saw that 100 participants are there. Firstly, it is a success of the conference. I am fully satisfied with the lectures of eminent scholars, research papers presented by researchers from different corners of the world. Physics theme of the conference at Urbana University, advances in physics. Physics is a major partner in International Academy of Sciences. Physics, chemistry, mathematics, these are major partners. And physics in itself, it is interdependent. So the topic here in this way, interdisciplinary, and this suits to the aims of IAPS, International Academy of Physical Sciences, interdisciplinary research in physical sciences. I believe that various lectures and research papers presented here are very much beneficial researchers, especially young researchers. I am thankful to Visionary Vice Chancellor of the university for giving permission, and I am also thankful to the fantastic convener, Dr. Ishwar Mule, and his entire organizing team work day and night for making this a success. Congratulate all of you and success of. In spite of being organized CONIAPS 26 successfully, we could not arrange award ceremony and memorial lectures. We have decided to 7 in the mid of two. I hope that the effect of COVID-19 will be minimized by that. We are receiving invitations to organize CONIAPS 7 from different reputed institutions of. We will take decision very soon and let you subsequently. Academy of Physical Sciences, I am grieved to let you that a patron and former president of the Academy, Professor B. Shukla, has taken his last breath in Varanasi. We have decided to dedicate the issue 20 of Journal of International Academy of Physical Sciences memory. This was published by the mid of December 2020, but because of decision, we shall delay the publication of this issue for 15 days, and it will be published by January 2020. You are invited to this issue. I hope that in 15 days, all the papers will be reviewed, and if they found able, they will be included this column, and this will be latest by. Once again, I congratulate all of you part of mega event 6 and hope that we shall meet again again in coming years. Wish you a Merry Christmas and a Happy New Year. Thank you. Jai Hind.
Thank you very much, sir. Now, without taking much time, now we move to the vote of thanks ceremony. So, on behalf of Gondwana University, Gadchiroli, and Indian Academy of Physical Sciences, I propose my vote of thanks to our Chief Patron, Honorable Vice Chancellor, Gondwana University, Gadchiroli, Professor Srinivasa Varkedi, for motivating us, for taking this initiative to organize the 26th International Conference of IAPS on Advances in Physics in their association. I'm also thankful to Honorable Pro Vice Chancellor of our university, Dr. Shriram Kavade, for his guidance in organization of this conference. I'm also at the same time thankful to the respected registrar of our university, Dr. Anil Chitade, for providing enormous cooperation in the organization of this event. At the same time, I express my thanks to the office bearers of the Indian Academy of Physical Sciences, Professor P.K. Bajpai, Vice President IAPS, and Professor P.N. Pandey, General Secretary of IAPS, for showing their confidence in us and providing an opportunity to host this conference. I'm also grateful to today's speakers, Professor Michael from Sweden, Professor Mohammad Ashkar, Professor Shri Ganesh Prabhu from TIFR, Professor Nilu Suryani from Udayana University, Indonesia, Professor Kishore Revatkar from Nagpur, and Professor S.C. Gedam, Professor D.H. Gahane for accepting our request and sparing their valuable time on Sunday. I'm also thankful to all the other speakers and chairmen of technical session and oral presentation sessions who were present for the first 2 days of this conference. I express my vote of thanks to all the participants who spared their time for 3 days. Now, I express my thanks to the convener of this conference, Dr. Ishwar Mohurle, for showing his confidence in me. I'm also thankful to the Joint Organizing Secretary, Dr. Mungmude and Dr. Panse for their constant support. At the same time, I'm indebted to the technical team, namely Mr. Devdatta Tare, coordinator of this team, and its members, Shri Krishna Devikar, Shri Shunil Chute, and Shri Pramod Borkar, for wonderful and uninterrupted technical organization and coordination. Now, with the permission of Chair, I declare that this ceremony of vote of thanks is over. Thank you very much.
हा क्लोज करा मीटिंग. Krishna, close the meeting.